Good morning, sir.
Hello, am I
Yes, sir.
audible?
Good morning.
Hello,
Good morning, sir.
audible now?
Yes, sir.
Morning, morning.
Audible, sir.
Just for taste, my voice is clear.
Yes, sir. Your voice is clear, sir.
Okay.
next 20 seconds, I'm going to tell you 15 things that you can teach online as a coach and make a lot of money from it. से बफिंग मशीन बोलते हैं। ये आपकी बात को समझा देगा। बफिंग क्या होता है? क्या होता है? सुना बड़ा तेज था ना? अच्छा है। इसलिए टाइल्स के लिए ना स्लोरी। मैं आपको बात की थी ना, वो ये घर का है, आपने गाड़ी नहीं? अब तो परेशान मत करो। सॉरी यार। मुझे आपका फेवरेट कौन सा है? ये वाला। इससे बढ़िया समय हो गई। आपको लंच में सी आया था क्या? नहीं, क्यों? मेरा फ्रेंड बिहार के। अच्छा, तो उसे नहीं। उसको साइंस टेस्ट में सी आया था। तो कविता मैम ने बोला आए तो बड़े होके बाकी एग्जाम पे पढ़ेगा। तो आपको भी क्या है? क्यों? ऐसा ना सकते। लेकिन ये होनी चाहिए कि कोई डॉक्टर बने, बढ़िया डॉक्टर बने। वो बात साफ करें कि तुम बढ़िया से साफ करें। काम बस दिल लगा के करें। तो प्रॉब्लम है क्या? ठीक है। अच्छा, तो आपने बताया नहीं कि बफिंग क्या होता है? बढ़िया वो चीज है जो शिद्दत से की जाती है। आपको बड़ा, छोटा या फिर सोच बनानी है। अब बताओ। इसीलिए college, 500 plus action. It gives you softness and relaxed special vibes. Softness is spoken back. Visit the nearest store now.
অরিন্দম, অরিন্দম স্পিকার। আরে স্পিকার অন করো। সৌরভ কোথায়? সৌরভকে দেখতে পাচ্ছি না।
দাদা আমি তোমাকে মিউট করছি।
ও আচ্ছা 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 আচ্ছা, থ্যাংক ইউ থ্যাংক ইউ। আই এম অন দি।
সুরদা শুনতে পারো?
হ্যাঁ 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 শুনতে পাচ্ছি।
শুনতে পাচ্ছি শুনতে পাচ্ছি।
এবার শুনতে পাচ্ছি।
Hello. Anshuman, am I audible?
Yes, you are.
Yes, you are.
Okay, thank you, thank you.
Am I audible?
Yeah. Absolutely.
Thank you. Thank you very much. Yeah.
Good afternoon to each and everyone. I should say actually very good day, because from across the country, across the world, different people, different fraternity, So each and everyone joined today's program, that third international conference on convergence of science, interdisciplinary science. Myself, Dr. Shobhan Ghosh, faculty of Department of Physics, ICFA University, Tripura, and this session today, the first session we are going to start now. The speakers and distinguished guests all are here with us. And before starting the day's program and this particular conference, we are going to start it with national anthem. And for that purpose, I'm requesting Dr. Anshuman Raishodhuri. He is present with us. He completed his MS and PhD from IIT Dhanbad, and currently he is in a position of research scientist at NUS, National University of Singapore. So he is an expert of chemistry of materials specially. I'm going to request Anshuman to start with national anthem, and for the national anthem, I'll be requesting each and everyone to stand up in your seat and just to start with your camera on, please.
Thank you. Jana Gana Mana Adhinayak Jaya He Bharat Bhagya Vidhata Punjab Sindhu Gujarat Maratha Dravida Utkala Banga Vinda Himachala Jamuna Ganga Uchala Vitaranga Tava Shubha Name Jage Tava Shubha Ashisha Mage Gahe Tab Jaya Gatha Jana Bharat Bhagya Vidhata Jaya He Jaya He Jaya He Jaya 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 He. Thank you.
Thank you, Anshuman. Thank you, each and everyone. Now we are going to start with our welcome speech of conference by the convener of the conference, Professor Arup Kumar Das.
আর একটা ভালো সে একটা প্রোগ্রামে আজকে তার রিপোর্ট করা আছে সেখানে
Professor Arup Kumar Das from IIT Roorkee, and I think Professor Das is present already. I have seen. Let me introduce him. He is currently working as associate professor at Department of Physics at IIT Roorkee, and he has completed his BE in mechanical engineering at 2003 from Jadavpur University, Kolkata. Later, he moved on to Kharagpur IIT, did his MS in thermal engineering, and after that, he continued his PhD from IIT Kharagpur in mechanical engineering. And from 2010, after completion of his work, he joined IIT Roorkee. His specialization area is multiphase flow, microfluids, and biofluidics, and he is the associate editor of Science Dialectica and also serving for this conference as the convener. Professor Das.
Thank you, Dr. Ghosh. Hello and welcome to all of you. I'm Dr. Arup Kumar Das. I'm from Department of Mechanical Industrial Engineering at IIT Roorkee. So, on behalf of the organizing committee of Third International Conference on the Convergence of Interdisciplinary Science, I have great pleasure in welcoming all the delegates in this online conference during today and tomorrow. That means 2nd and 3rd March of 2024. After the inception in 2022, that means last 2 years, this year, this is the 3rd version of the conference series is being organized by Science Dialectica. This conference has been patronized by Scentia Research Foundation and SRF Global Foundation. Last 2 versions of the conference, though we have organized virtually, I was part of both the conferences, but it has attracted several academic and industrial researchers, participants in the field of advanced scientific and engineering product development. This year also, this is a 2-day conference, virtual conference we are having. I feel that this will cover the entire scope of the scientific innovation and fundamental research. There are around 17 invited talks. So far, I have the news from the ground level organizers and 2 poster sessions displaying a wide variety of research topics. Besides, there is a special talk by our chief guest, Professor Manoj Mitra, former professor and dean of Jadavpur University, but from I have also done my BTech. At the end of the session, participants from junior school will be also taking part in scientific quiz contest, which we have organized to have a better introduction between the school children and the eminent speakers. During the sessions, experts from academic institutions, public sector undertakings, and private sectors will directly interact with the participants. Major cornerstone has been the several top scientists in their field will be delivering their valuable thoughts on subjects like nanomaterials, energy, and their sustainable applications, along with the related discussions. There are many researchers who are attending this conference every time. I have seen some of the names I have seen being repeated, which itself shows that it is getting respectable inputs. They are getting respectable inputs from the speakers in the conference in the different research directions. I'm confident that you will also enjoy this motivating conference talks, and I know that your presence and participation will add to the further surrounding the subject and improve discussion, fostering new ideas, and will be bringing collaborations. Though I understand that at the end I'll be also getting some time to speak, but I want to thank in this moment only in advance to all the supports, whatever extended by the speakers and participants for their efforts. And I believe that this conference will be a great success, and then it will be a good interaction between all of us. At the end, I wish that Science Dialectica will keep on growing in coming years with more impact on the national and international research community. With this, I would like to conclude and go ahead with the other presentations. Dr. Ghosh, over to you.
Thank you, Dr. Das. You have actually very nicely introduced this particular conference. 2 years back we started, and Science Dialectica and Scentia Research Foundation, we are trying to just cater the knowledge, and not only knowledge, better to say, to bring out the interdisciplinary things amongst the students, and throughout the society. So in that aim, we have started this particular work. And now I have something to tell you that's not so good news for us, that our chief guest is not present and he is hospitalized. Just now I got the message. So he will not be there for today's program, I think, but I hope he will be recovering very soon, and after that he will join us. In that case, I'm going to request our Saurabh Kanti Jana, Professor Saurabh Kanti Jana, to talk about this conference and the SRF. Fine. Dr. Saurabh, he obtained his PhD from on Italian University, and he is now working as senior scientist at IIT Madras. His research topic is specialized area on nanomaterials for optoelectronics and energy gas sensors. Current research topic on the development of electrochemical sensors and handheld instruments for digital education. Dr. Saurabh. Dr. Saurabh, are you there?
Yeah. Thank you, Shobhan. Thank you for introducing me. Just let me share the screen. Just give me some time. Okay. Thank you. Because I was not aware of that that our chief guest was hospitalized. Just now I got this message, so I conveyed that message to you. So just give me some time. Meanwhile, I just share my. Thanks. My screen is visible?
Just. Yeah.
Full visible? Full screen?
Yes, it's coming. Sure.
No, just let me know that it is full screen or not.
Yeah, it's full screen.
Full screen only? Okay. Shall I start?
Yeah.
Okay. So, welcome. Good morning and good afternoon and good evening, where you are. On behalf of organizing committee of Third International Conference for the Convergence of Interdisciplinary Science, so I call it as IC square IS, not IC2 IS. So, and I welcome all distinguished professors, scientists, postdocs, research scholars from the various institutes of India and across the globe. I also welcome all the editors and all the scientists of scientific committee and the members of Science Dialectica and Scientific Research Foundation. So, in next 10 to 12 minutes, I will be discussing about the journey of our organization from scratch. So I can call my talk as a beyond the blank canvas, a journey of SRF from concept to cosmos. So I would like to mention that it will not be a scientific presentation. So how we'll grow from a concept and how this organization becomes after 4 years. So I just will want to share our story.
Saurabh, your face is not visible, so if you can adjust.
Yeah, Saurabh, if you can show your face, it would be looking nice.
Now it is coming fine?
Yeah, fine.
Okay, thanks. So in 2020, just go back in 2020, when the whole world was struggling with coronavirus. And like me, I think all of you are struggled that time also. So when no physical meeting was possible with anyone, only wearing mask, and we had to stay in home and stay safe. So we had only medium to communicate with all the people with internet or phone. So like some other day, I got a call from my close friend. I don't want to mention his name right now. So we discussed many things as usual on the science to politics, society, and education, etc., etc. So suddenly he asked me, "Can we do something new?" So I told, "What will you do? We just we can just." Only can chat or something. Otherwise, in this pandemic time, what will you do? So and but his means that day his talk is means what he told, that some depth was there. No, we have to do something. Okay, then we are started thinking day by day, and okay, and then one day we came up. Okay, let's do something so that from home or from home we can do popular science like that. So and how will we start this one? So maybe we can start in writing this thing. So we started writing, and we started writing some scientific topics. So then our this new platform, the Science Dialectica came. So I hope someone means some of you maybe have seen this platform, Science Dialectica, and it is SD. So you can visit us. This is our website, sciencedialectica.com. So this is our website. And then we started first news article we published in 2020. So if you see, this is the date, 25th August 2020. So when the whole world was struggling. So first the news title was "The Pandemic Named COVID-19 India Beyond 2020." So the article was written by Sayan De. That time he was a student of IIT Kharagpur. Now he is an assistant professor of IIT Bhubaneswar in electronics department. And then in 2024, now see in 2024 the recent news in cracking the code of the brain. So by my dear junior friend, my friend. So his name is Dr. Pillalamari C. Krishnarka. He is doing right now in postdoc fellow in Tampere University, Finland. So he has been doing tremendously well because he write so many news articles for us for a long time, and he has been doing tremendously well for us right now. So presently he is also in news editor of Scientia Research Foundation, which is SRF. So and then initially and then we cater our vision. So what we can do further. So initially we tried, okay, let's do something, whether because in our we are academician, we don't know what industry are do, or industry doesn't know what academicians are do. So let's create a platform. So where that both industry persons and academic persons can share their knowledge, so that we can share the knowledge and problems, what we are doing, what they are doing, and so that all together can do. So that is our also initial visions. So with that visions, we started this Science Dialectica journal. So Science Dialectica is a journal, is a magazine. So I am sharing you is a journal section. So this is the journal section of the Science Dialectica. If you see, there is a it looks like a conventional scientific journal page. So where the editorial team are there is a submission, review policy, author guidelines, archives, plagiarism policies, everything is there. So the guy, we are fortunate, the guy who published the first article with us is Kaushik Bagani. He was a PhD student from Saha Institute of Nuclear Physics. He published from Switzerland, and this article we received at 2021. But due to some official things, and then we publish it 2023. So you can get this article through this link. So if you see that this is the abstract, and you can cite that article like this, and also also we are in a process to get in Scopus. So this is the current status of these journal sections. We have digital object identifier already. and we are just about to get that ISSN number of that particular first issue of that of the journal, and then we will get that UGC approval pending, and it is a Google already Google Scholar it is cited, and obviously the cross reference it is there, and Scopus and that PMC it is under process. So it is almost we are ready to become an international standard journal. So I request all the distinguished professors and students who are present here, please join us and make this platform to a broader vision. So that because we are always think about ACAs, APAs. So why not we should publish a journal from India? So why not a journal house from India? So like ACAs like that. So I just request everyone to join and participate and publish something with us. Not I am not expecting, and we are not expecting that journal, I mean that science which you are doing right now, but you can publish with us just recent development on your topics, or what the current scenario on Indian context, and how the Indian science is growing, like that. The different topics you can publish. I am not expecting that original research results. So this is my request to all of you. Okay, then we are also growing in other directions. Hello, excuse me. Excuse me. Can you turn off your mic? Excuse me. Turn off your mic, Arindam, please. So we are also in a position to publish in a book. So last year we got a ISBN registration. So we published our last abstract book of this conference like a book. So this is the ISBN number of this book. So you can get so, and also we have that RNI number, so that we can be we can have an authority to be a news publishers in the book publishers. So we designed this platform for everything, like for education purpose only. So in different for the different education purpose. So our vision was there, and then our future plan on this platform, that how to write the popular science writing. So this science can be for all for common people. And also recently we have planned to write something in title of What You Say. That means in your professional area, in your lifespan journey, you may have something gather some experience. So please share with us with some positive thoughts and positive impact on that. Something like that. Some positive message should be there. So that you can convey with us and share with us. So like that, we want to publish like a story of the month. So based on that, that your message or something, we will maybe publish like a story of the month. That story can be published through this platform. So likewise, we test our what the capability to in the broader directions. And then, okay, so then what will we do if we have this science dialectica, and then that our core members also wanted to do some research and something. So on view of that, okay, let's do form a non-profitable organization, so that we started an organization like Cynthia Research Foundation, which is SRF. So under the SRF, we started that education for all. For that, we set up a organization like Cynthia Education, and Science Dialectica already I have mentioned, and also that as a product or as a so we also organize that SRF Tech. So what our key vision is that right to get space for free thinking on science, reaching the science for every common people, and build a self-reliant and sustainable economy model for village through involving commons in research activity by exploring creativity of individual. And our strategy is that publishing popular scientific journal, frequent free thinking workshop at school level, state-owned school, and building an interdisciplinary laboratory, in particular a village, starting a mother education movement through communication training for below poverty level family, finding the strength of a particular village and making opportunity for them, and making self-reliant laboratory, and publishing different books on information of advanced scientific and opportunity and events. So, and also under Cynthia Education, we have planned already. We have been doing something, some activities going on. So we created an AI hub, and one project intern is still he has started. He joined in last year December. So he is working on artificial intelligence and machine learning. And also we are doing some research. So how this artificial intelligence can be used as a drug design. So today, day after tomorrow we have a presentation from our side. So on how this AI can be used as a drug design. So new drugs can be designed using AI, not that conventional AI which is already in market, not ChatGPT. In ChatGPT, you can get information. This is a text-based AI, but in the AI, where we can design the algorithm, so that using that algorithm, one can design the drugs. And also in this artificial intelligence, how we can implement in material science research. So likewise, we have started this thing. And our friend, he is also master of that. Along with that, this intern is working. So both two, they are working very hard, and something we will come up in this year. And also we have designed some professional courses like Python, basic, advanced SQL, advanced Excel, Power BI. These are the where those who are business professionals who are doing for corporates, they must learn this kind of AI, advanced Excel and Power BI. So we will design a course. So and we have a plan to offer a certificate course in collaboration with North Bengal University, which is actually this process is going on. We have started discussing with the vice chancellor of this university. So that process is going on. And also we have already planned and started some activity on this. So robotics and science project in school students of India. If you see this girl, she is my daughter actually. She is doing home and she is enjoying when she is in class 5. So she is in class 4 and she is doing some activity on the electronics. So like that we can design science project, and so that village students, they can learn, they can do also, they can enjoy the science, because this kind of facilities is not available in village. So basically, not only our focus is not only the rural area, urban area, as well as basically our focus is to grow, spread our vision rural area. And now also there is another activities going on, which is the biomedical device. We develop a device that is Suhridoy, an AI enabled device for monitoring healthy heart. So this project is actually going on with in collaboration with AIIMS Kolkata. Basically, it's under testing stage. So hopefully, at the end of this year, it will be a prototype, or it will be it's kind of a first stage of this device. So let's see how it can help to that rural area people, those who are suffering in cardiac arrest at night. So where there is no hospital, only some local hospital, local that clinic. So we have this kind of vision, and also there is already a product with a green lubricant, which is actually this product already we developed, and it is also in under testing and validation in industry. Industry in basically this is testing going on in jute industry. And also it's a nanocellulose is another product which is actually we are already started. It's under R&D, means we are doing in laboratory test. So we'll be starting also in bulk production. So some characterizations and material, that how it stabilize, how it can be stabilized, this nanocellulose, because this nanocellulose is a big market in 2025. So with this, without all these things can be done only possible because people who supported us from the day one. That is our editorial team, who gives us a constant support and suggestions, and is a scientific team with a dynamic and enormous effort of them, and also the core operational team of this organization and the founding members. And also, I would like to mention specially few names with Professor Arup Kumar Das, who is the convener of today's this conference, and Professor Abhishek Chaudhary, Professor Arghanaran Banerjee, Professor Sayan Bayan, Dr. Ratan Sengupta, Dr. Runima Bondapadhyay. Also, I want to mention some few others names who is really doing hard work for this organization. Dr. Arpan Bhattacharya, Dr. Sitama Mukherjee, Dr. Rangsuman Ray Chaudhary, Dr. Pillamari Krishnarka, Dr. Montu Modak, Mr. Somodi Mandal. Actually, I mention this name without any hesitation. At a moment, if I ask him to do something, he is ready to deliver it. I just use I can tell this, I just use him actually. So he's really obedient, and he's really doing that without any expecting anything. He's doing for us, for these websites, how these journal can be designed. Everything he is doing for us. And Mr. Rupong Sarkar, he is actually the intern who is doing these AI related projects. And Mr. Amoga Parsakini, he actually is a current PhD student at IIT Madras. He is help us in terms of designing and how we are this conference is going on. This kind of design he is giving us some plans. And finally, I want to mention the man who called me the first day that let's do something. He is the founder and chairman, and Mr. Sudhanshu Bose. So without his knowledge and with his business, we could not come up with at this stage. So with this, I conclude my presentation. I think I take some 10. Okay, I am in time, right? So on, and thank you all.
Thank you, Saurabh, for presenting entire things of SRF and Science Dialectica in a nutshell. And now it's the time for us to proceed for the second session. And for the second session, we have so many.
There is one raised hand by Mr. Pradeep Shamanto. You may listen to him.
Yes, Pradeep Shamanto, if you have something. Pradeep Shamanto, I think it might be by mistake. So I thank all the speakers, Professor Arup, Dr. Saurabh, and Dr. Rangsuman for this session. And I'm going to hand over the stage for the next session to Dr. Sritama Mukherjee. Sritama is there, and just I'm going to introduce her before concluding my part. So Sritama is presently working in University KTH, Sweden, and she is already showed up told one of the founder members and regular supporters. Entirely, she is working for Science Dialectica and SRF. Sritama, please, stage is yours.
Thank you, Professor Shobhan, for this nice introduction. It has always been my pleasure to stay connected with SRF and SD, and to be able to support them in whatever small way I can. So a very warm welcome again to everyone to this conference. And without further ado, let's proceed to the keynote speaker of today, Professor Purushottam Chakrabarty. He was former senior professor of physics in Saha Institute of Nuclear Physics, Kolkata, and former adjunct professor of physics in University of Pretoria, South Africa. Um, he has a lot of things on his cap already. I will try to give a brief introduction. Um, um, so, considered one of the world's leading experts on materials analysis using ion beams and secondary ion mass spectrometry, which is SIMS, Professor Purushottam Chakraborty was awarded the most eminent mass spectrometrist of India by Department of Atomic Energy, DAE, Government of India, and conferred the gold medal by DAE for his meritorious and outstanding contributions in SIMS. He has received the prestigious Premchand Roychand Scholarship PRS of Calcutta University for indigenously fabricating a radio frequency quadruple mass spectrometer for the first time in India. His research area is quite vast, as I can see. It includes atomic collisions in solids, secondary ion mass spectrometry (SIMS), secondary neutral mass spectrometry (SNMS), molecular ion SIMS, X-ray and ultraviolet photoelectron spectroscopy (XPS and UPS), O'Shea electron spectroscopy, and so on and so forth. Professor Chakraborty's recent work on metal glass nanocomposites has led to the remarkable achievements in the development of novel photonic materials, thus opening the way for advances in all optical switching, coupled waveguides, and optical computation. He has received a lot of accolades, awards, and recognitions. He is a fellow in Indian Chemical Society and West Bengal Academy of Science and Technology. He has also been visiting professor in IIT Tirupati, Tezpur University, and so on. And he has delivered invited lectures and chaired at more than 160 national and international conferences across the globe. He has published more than 150 scientific papers, including invited reviews, monographs, our conference, and I would like to
अब क्या करोगे? Love you, John. I love you so much. তোমার বর্তমানে পাগলের মতো ভালোবাসে, পাগলের মতো। সারাদিন ইচ্ছা করে এরকম জড়িয়ে রাখি, চুমু খাই খাই। মাথাটা বুকের উপর দিয়ে রাখি, সারাদিন এরকম দিয়ে রাখি। I love you. I love you so much. এই যে ঠিক আছে, শুধু তুমি দেখাবো। সোনাটা Gulu gulu. Surface Physics and Material Science Division. কি দেখো? একটা ভালো গান চালাও না, একটু শুনি। ভালো একটা গান চালাও, ওই গানটা চালাও, যেন তোমারই কাছে। বাংলা গান চালাও, যেন তোমারই কাছে। যেন তোমারই কাছে। মন খারাপ পারে তোমায় ফেরাতে, এসো মনের কুল কিনারে বেড়াতে। এক সেকেন্ড দাঁড়াও, হ্যাঁ। টক বাই টক করতে বললে এটা শেষ হবে, এরপরে এটা শেষ কটা হবে? 1:13 বাজে। যে- এই গানটা আমার খুব পছন্দের গান, আমার দারুণ লাগে এই গানটা শুনতে। 2:15 ওকে, 2:15 থেকে আর একটা হবে। ঠিক আছে, 2:15 থেকে 2:15 ঝুমে অভিমান আছে কাছে, ঝুমে অভিমান। এটা সেতারের আওয়াজ। আরে ये लुक तुम्हारी पागल ना हो जाऊं मैं ওই গানটা চালাও যেন তোমারই কাছে তারপর হচ্ছে তোমার ওই গানটার নামটা হচ্ছে ধরো আরে আরে সেই ইয়ে আছে না গানটায় শ্রাবন্তী আছে আর হচ্ছে তোমার ওই চেটে চেটে হরলিক্স খাবো ওই মালটার নামটা কি? সোহম সোহম আছে ওই গানটার সে একটা অনেক আগে ওদের কচি বয়সের একটা গান আছে না সে ফান্দে পড়িয়া না হ্যাঁ ফান্দে পড়িয়া বাবা কান্দে রে মনে হয় সিনেমাটার গানটা না তার আগে অন্য কোনো ইয়ের গানটা অন্য কোনো সিনেমার গান মনে হয় গানটা কি নামটা ভুলে যাচ্ছি ওই গানটা ভালো লাগে ওই গানটা ইয়ে গেছিল বলছি নামটাই তো মনে করতে পারছি না দাঁড়াও সুরটাকে মনে করি আহ, গানটা এটা ছিল মেসেজ করে যাচ্ছে রেকর্ডিং ঠিক হচ্ছে তো না আপনি করুন এসে আমি ঠিক করছি না আপনি করুন আমার চেয়ে বেশি জানেন সেট আপ করলাম আমি আপনি জানেন একটা কাজ পারে না আবার মাথা গরম করে দেয় মানে সেট আপ করলাম আমরা দুজনে মিলে বসে ওনাদের একটা একটা সেট আপ ওনারা করতে পারে না উনি আবার আমাকে 14 বার করে মেসেজ করে জিজ্ঞাসা ঠিকঠাক হচ্ছে তো এই গানটা বলো দাঁড়াও দাঁড়াও সোহম আর ইয়ে আছে না না এইটা না আরে ওইটা সার্চ করো না ফান্দে পড়িয়া বাবা কান্দের দেখো একবার ইউটিউবে গানগুলো কি কি আছে অল সংস বলে একবার ওই সিনেমাটার দেখো তো একবার কি কি আছে রোমান্টিক সংস ও এমনি সার্চ করো জাস্ট রোমান্টিক সংস অফ শ্রাবন্তী অ্যান্ড ওর নামটা কি সোহম দেখো প্রথমেই মনে হয় দেবে ওই গানটা দেখবে শ্রাবন্তী একদম কচি একটা নীল জামা পরে একটা ইয়ে ওটার মধ্যে ইয়ে করছে হুম 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 বেঙ্গলি প্রেজেন্টটা খেয়া করো পার্টিসিপেন্ট খেয়া করো মানে পার্টিসিপেন্টদের প্রেজেন্ট রেকর্ড কি করে করবো প্রেজেন্ট কি করে আবার নেবো এটা কি ইয়ে নাকি স্কুল নাকি স্কুলের বাচ্চা নাকি যে প্রেজেন্ট নেবো কত এদের এক একটা ইয়ে প্রেজেন্ট রেকর্ড করো ওইটা ইয়ে নাই ওইটা চালালো না গানটা ও মাই লাভ শ্রাবন্তী বলে সার্চ করো না ও মাই লাভ শ্রাবন্তী বলে বলো ও মাই লাভ শ্রাবন্তী ও মাই লাভ শ্রাবন্তী ঘড়ি থেকে ওয়ার্নিং দিচ্ছে ইয়োর বিপি ইজ টু হাই Okay, Devi, hold up. দেখছি এটা অডিওটা একটা জায়গায় তো স্ট্রিম হচ্ছে, কিন্তু এটা এক্ষুনি আমার আবার কল আসবে। ইউটিউবে স্ট্রিমিং কেন হচ্ছে না? এদিকে দুইখানা কেউ ওটা খুলে বসে আছে মাঝখানে। ওরা ইয়ে করবে। করুণে ও করুণ, বারণ মনে পড়া বারণ। কারণ কি জানি মাঝখানে আবার কেউ এ বাবা এ তো ভিডিওতে সব আমাদের কথাগুলো যাচ্ছে গো রেকর্ড হচ্ছে আরে এটা বলে দেবো যেটা ইয়ে এমনি তো ভিডিও বন্ধ হয়ে গেছে তো কি সেট আপ করেছে আমি বুঝতে পারছি না ও সেট আপ করে দিয়েছে আমার তো এটা কিছু ইয়ে নয় যা সেট আপ করার ও করে দিয়েছে ওকে অ্যাক্সেস দিয়েছিলাম ও করেছে
having the highest detection sensitivity. It means amongst all the techniques known to us, SIMS secondary ion mass spectrometry can detect the lowest concentration possible one can think of. That means sub parts per billion. If you have one atom, if you have one or a few atoms of carbon in silicon, somewhere in the silicon, maybe on the surface or somewhere at the middle or somewhere at the bottom or somewhere at some depth, you can pinpoint the quantity and the lateral distribution and the quantitative distribution of that particular impurity element in the material by the secondary ion mass spectrometry. Okay. Now, actually, what is SIMS? I'll be talking first what is SIMS and what is the matrix effect. What is the alkali based? The cesium is an alkali. What is alkali based molecular SIMS? And what is MCS? N N can be 1, can be 2, can be 3. So this is a molecular SIMS, molecular ion complexes, very difficult to form because the detection sensitivity of the molecules is extremely small unless your machine is having extremely high detection sensitivity. It is impossible to detect MCS N kind of molecules. Okay, and now how do we do MCS molecular ion SIMS, and how do we do interface analysis of quantum structures using this kind of MCS molecular ion SIMS? SIMS in SIMS, basically an incident ion is coming. So it is could be oxygen, could be inert, like argon, krypton, xenon, radon. It is an inert gas, or it could be cesium, it could be oxygen, whatever it is we are doing it is the projectile. So with some energy, it could be some 1 kV to 2 kV or 3 kV, depending on what kind of energy we want. But the energy, some energetic particle is bombarding on the material. Okay, this is the top surface. You see, these are the atoms. Now, when the primary ion is incident, so up to this point, the energy was not changed. But when it enters the material, the energy is gradually dissipated essentially because of the energy, because of the collisions, because the primary ion, the red one is the primary ion track. The primary ion is hitting some target atom. This is the target atom at some layer. Maybe it is the third layer. And this target atom, what happens? The primary ion, the track can be changed, the direction can be changed because there is a momentum transfer, and so it can be scattered and it is elastically scattered, and this target atom can have a motion. After getting hit by the primary ion, it is suffering another collision. So and the secondary collision is starting, and the secondary collision is again they're hitting more atoms, and the tertiary collision starts. So eventually there are many atoms. Practically there are innumerable atoms in the target material. They are all set in motion. So there are huge number of collision cascades. Okay, I'm talking about a single collision cascade where there are many atoms are in the collision, and there are multiple collision cascades can happen. So due to a single primary ion, there is a single collision cascade, and thus for the second incident ion, another collision cascade, depending on the number of particles, flux, depending on the flux, actually, whether it is the collision cascades are overlapping, are getting overlapped, or they're independent. I will be concentrating, I'll be thinking that every collision cascade is independent of one another. Okay. Now, basically what happens, you can see the primary ion is hit on the top surface, and the atoms are ejected. How they are ejected? Because the collision cascade is happening. A part of the collision cascade, finally, they are moving from the bottom to the top, and they're eventually arriving at the top surface. So the momentum transferred by a part of the collision cascade is received by the top atoms, which are sitting on the topmost atomic layer of the surface. And if the surface binding energy is more, the surface binding energy of the topmost atoms is more than if the transfer of surface energy from the collision cascade is more than the surface binding energy, then some of the atoms from the top surface can be ejected. Now, 2 atoms can be ejected, or 3 atoms can be ejected, or even the different number of particles can be ejected. Now, if there are different number of particles, this is for example a single atom or atomic row. This could be a single atomic row, another kind of atomic row of another element. So and if we go on making the bombardment goes on and the ejection goes on. So basically you can see there is an erosion. So the erosion has to come. As you can see, some of the atoms from the top surface have been eroded. So essentially you are etching the top surface. The top monolayer has been eroded. And if we go on bombarding, the second monolayer will be eroded. And if we go on bombarding, the third monolayer will be eroded. So essentially, we are eroding layer after layer, layer after layer. So it is a consumptive process. You are consuming the material of the whole material. The material, a part of the material has been consumed. So it is a destructive process. But then why do we do SIMS? Because the detection sensitivity is even sub parts per billion. So in the semiconductor industry, people are, it is indispensable mechanism, indispensable method of making analysis, because one has to know the dopant concentration. Okay, indium is doped in silicon to make an okay, the positive the p-type semiconductor, or if you dope phosphorus, you dope you make the n-type semiconductor. Semiconductor people have to know the dopant concentration. Semiconductor people have to know the dopant distribution at a function of depth. So SIMS is essential. So it is a consumptive process, of course, but it is compulsory for all measurements, for compulsory measurement for all semiconductor people. Essentially, what we measure basically the particles what are emitted. They are coming from the top surface, 1 or 2 or 3 monolayers, because the collision cascade is happening and it has a large jurisdiction of about 100 angstrom thick diameter, the collision cascade. But the part of the collision cascade which is reaching here, they are essentially ejecting the topmost atomic layers from the top surface. So it is basically surface analytical technique. I have to go quickly. This is, you can see there are many collision cascades. They can be independent, or they can have overlapping. I have to go on a little bit quicker, and you can see this is the secondary ions. I should tell you the number of particles which are ejected. They are called sputtered particles. They are called sputtered particles. So 99.99% they are all neutral particles. So 0.01 or even 0.01% of the sputtered particles or ejected particles are either positive ion or negative ions. So we are detecting those positive or negative ions, which are essentially coming from the topmost atomic layer by the mass spectrometer. It could be a sector magnetic field, or it could be a dynamic type of, like a quadrupole mass spectrometer. Whatever it is, we are using a mass spectrometer followed by the detector. I have to skip. Only thing I can tell you that essentially we can find out this is the sputtering yield or sputter yield. That means number of particles ejected due to a single primary ion impact. And this is one expression can be understood that this is basically x1 is the effective thickness of a sputtered layer. That means the thickness of the top layer is x1, effective thickness, and W0 is the number of the particles which are being ejected. They have the energy, they have the kinetic energy. So they have the average kinetic energy of the particles which are ejected is W0. So this is typical energy, and this DEDX is called the nuclear stopping cross section. Okay, this is basically DEDX is nuclear stopping, the rate of change of energy with respect to the distance, with respect to the depth. Why it is nuclear? Because it is the energy of the particle, energy of the impact particle, energy of the projectile is much less compared to the velocity or energy of the electrons which are rotating. So the velocity of the incoming ion which is being projectile, which is used as a projectile, the velocity is much less compared to the electronic velocity in the orbital motion. Naturally, the particle will not see the electrons. Okay, the particles will not see because they are not coming into the same, because when they are comparable, then the question comes that there will be interference or something like that. Oh, so basically it is hitting the nucleus. So it is seeing directly the nucleus of the atom. So it is a nuclear stopping cross section. Depending on the energy of the primary ion, primary projectile, the electronic stopping cross-section can happen where the electron cloud is disturbed, where the electron motion in the cloud of the electrons disturbed. Okay, so it is, and as you can see from the expression, the thickness is something like 0.25 angstrom from the two expressions, which is about even less than 1 angstrom. So basically, this is a hypothetical, of course, from the calculations, but theoretically, it is about 1 to 2 angstrom thickness, what we are talking about in the Sims measurement, that is the top monolayer thickness. I have to quickly go on to the modes of analysis. There are two modes of analysis. One is the static Sims, another is the dynamic Sims. The static Sims means the primary ion flux is too small. It is the picoampere per centimeter square, the current density. So therefore, you can imagine the erosion rate of the material is extremely small. So you are essentially doing an experiment for an hour. You are essentially stuck to 1 or 2 monolayers. So you are not damaging the material. So it is the static Sims. So basically, you are not going deeper. Okay. So you can see we are essentially confined to the top surface during your entire experiment. Okay. Only the top monolayer is, we are confining the top monolayer, unless we go to the dynamic Sims, where the primary flux is much more, microampere per centimeter square, and the erosion rate is getting too high, and then we can really erode the materials. We can etch the material, that means the material layer by layer. This is the mass spectrum in static Sims. And you can see in the dynamic Sims, where the flux is more, the current density is more, then we are essentially going down and down and down, because one monolayer has been removed, the second monolayer has been removed, because the bombardment time is going on. No, the bombardment is going on. We are continuing the bombardment with the primary ions. So essentially, we are going down and down and down. Now you can think of a particle somewhere here, for example, some kind of carbon, or say aluminium somewhere here. You have to go down to that level. So that means you have to go to the depth profiling by dynamic Sims. And obviously, as you are consuming more amount in the dynamic Sims, the sensitivity is much more. As you are consuming much less in the static Sims, the static Sims has less, the sensitivity, the detection sensitivity is much less in static Sims, but in the dynamic Sims, the detection sensitivity is much high. This can be seen from a very simple expression, that the detection sensitivity is going up. For as you erode layer by layer, the detection sensitivity is going up as you go on layer by layer removal. This is just an example. Sorry, this is just a schematic diagram of my machine. I am using a quadrupole mass spectrometer, which is a dynamic type of mass spectrometer, because this is there are ions. Here there is no magnet. Remember, this is a mass spectrometer, but without any magnet. So there is no magnet actually separates as per the momentum, isn't it? Because the Lorentz force is there, and so depending on the momentum, depending on the mass, and so there you are having different tracks in the magnet. So the track of the curvature of the ion which is passing through a magnet, they are changing in a magnet, and you are getting the different kind of particles, or depending on the masses. So mass separation is possible in the mass spectrometer, but in the static Sims it is using a magnet. Sorry, in the sector magnetic field you are using a magnet, but in a quadrupole it is a quadrupole, where ions, the secondary ions from the target, they are moving. They are oscillating and oscillating, and they are transporting. So the transportation and the oscillations are going on together. And of course, there are two things possible. The ion can be lost by collision with the rods. These are the stainless steel rods, making a quadrupole. So this is a quadrupole, which is a length of a certain length, of course. And at the end of the quadrupole, you have a detector. and so you are actually detecting the secondary ion after getting transported. Now, if it is lost, it means you are not able to detect them. So depending on the stability diagram, so I'm not going into detail, but on the stability diagram will dictate what is which mass will be stable, which mass could be ultimately transported to the end of the quadrupole without suffering any collision with the rods. I'm not going into that part because this is all technical. This is the machine of my laboratory. This is a secondary ion mass spectrometer, and this is the another version of the secondary ion mass spectrometer coupled with the secondary neutral mass spectrometer. Okay, we are also able to detect the secondary particles which are not ionized, which are also the neutral particles. I should quickly tell you to just because I'm not taking time, just to say you. So this is very there are for many years people had worked on the mechanism of the secondary ion formation, because it's a very complicated process. The sputtering is much more simple. The number of particles which are ejected due to the impact of primary ion is very simple to understand. Okay, but how the ions are forming, how many positive particles, how many neutral particles are losing the electron to get ionized, how the ionization probability, how the degree of ionization, or how the ionization cross section is, that is very crucial factor which is very difficult to understand. And I could tell you, we have been able now to understand much better the mechanism of secondary ion formation. Initially, the people worked with the Saha equation. In a way, Meghnad Saha gave the equation to understand the temperature of the solar system, or like the sun. So he gave the first equation for which Meghnad Saha became so popular, so famous, and so famous in astrophysics. So he, in fact, said that the ionization probability, so the number of particles which are ionized and number of particles which are neutral, so the ratio is the ionization cross section that is given by the expression. Okay, where these are of course the terms have their meanings. Of course, m is the mass of the electron, k is the Boltzmann constant, h is the Planck's constant, t is the temperature, u is the partition function of the material, ux is the partition function of the element of interest which you are detecting, and ne is the electron density, and exponential ix the ionization potential of the atom of interest. And because it is a plasma, in the solar system, it is a plasma, high temperature plasma. So the ionization potential is depressed, is reduced. I'm not going into that, but this expression was applicable in understanding the secondary ion formation mechanism in the SIMS. But of course, it has limitations. I'm not going into that. We have worked a lot about the secondary ion kinetic energy distributions. So by measuring the kinetic energy distribution of secondary ions, we can say that this mechanism was a failure. First of all, the atoms, ions, all are in the plasma, local plasma. They are all in the thermodynamical equilibrium state. But so essentially, all particles have to follow the Boltzmann distribution. Okay, isn't it? So all the particles in the plasma of the sun, or the plasma of the heat of the point of impact, where the particle primary energy impact particle is hit on the top surface, it's forming a local plasma on the top surface. Essentially, it's a plasma on the top surface. And so the particles which are emitted, the positive particles, the negative particles, electrons, the neutral particles, the photons, everything are in the equilibrium state. So if you measure the kinetic energy distributions, they have to follow Boltzmann distributions, isn't it? But it's not. In the SIMS, it is a drawback. The expression failed, but I will not go into detail. This is an expression for the secondary ion current intensity from where we can measure the concentration of the element. This is the dopant concentration, where these are all constants. This is the degree of ionization, how much ions have been converted from the neutral particles to the positive ions or to the negative ions. X is the element. Say carbon, for example, in silicon, X is carbon. Say silicon is containing aluminium, then X is aluminium. So beta X is the degree of ionization of aluminium. Very, very crucial. This is important because this is very difficult to understand, to measure. Nobody could measure beta X. Okay, I can tell you that my student and myself and my previous student, we have been able to measure we measure this kind of degree of ionization by making the work function, by making the localized work function instantaneously changing at every moment of during secondary ion emission process. And we have been able to measure the degree of ionization or ionization cross section at every point of time because it is changing instantaneously. Okay. I have not so much time, but this is the positive ion which is coming. So depending on where the positive ion is, from the surface, the positive ion, if it is here, the Fermi level, and if the energy is matching with the energy of the positive ion, which is being emitted from the top surface, and depending if it is on the ionization potential curve is like this, depending on the vacuum, this is the vacuum level, and if depending on the distance of the primary of the ion, secondary ion, so the energetically you can see when the distance of the positive ion which is being emitted, they are coming at this point, then the electron of the Fermi level, okay, they are matching energy of the Fermi level, matching with the energy of this. This has the spread is because of the uncertainty principle, because energy has a width, in the uncertainty principle, and we can measure this kind of width. Of course, I'm not going to that. So the electron from the Fermi level can tunnel to this where, and the ion can pick up an electron. The ion can pick up an electron, can be neutral. So the ionization probability depends on where your positive ion is located. So actually it is a very surface sensitive, because surface sensitivity means if there is a single slight oxidation or slight carbon or slight kind of any kind of light, so the Fermi level changes abruptly. I should quickly go that we have there are as I told you that the beta, the degree of ionization changes because it is changing instantaneously, okay, and therefore it is difficult to measure. Now we have been able how to quantify. Now you can see what happens actually. We have, you can see this is what I'm going to talk now. Just I will take 5 minutes more, or 5 to 7 minutes more. This is the alkali element. The alkali element is forming with the element of interest. What you are measuring, you want to measure the concentration of M. M means here carbon or anything like that. So the A is the alkali element. It is cesium or anything like that, or rubidium or sodium or potassium, whatever it is. So by using alkali ion, we are able to form MaN. N is 1, 2, 3. So this kind of molecules can be possible to form in the secondary ions, but as I told you, very difficult to get the estimation, or because their intensity is too small. What happens, you see when you grow a thin film of gold, if you grow a thin film of gold at the interface, this is the depth. At the interface, you have a high peak. This high peak, you are measuring the gold signal by SIMS. The high peak is coming at the interface because your gold film and the interface, because you are growing a gold film on gallium arsenide, and at the interface, the dotted line is the interface, and this interface was having a slightest oxygen concentration, and due to the slight oxygen or slight oxidation, there was a hump of the gold signal at the interface. This is called the matrix effect. And as you can see, when we take the MCS, gold cesium plus, this is the gold cesium plus, the E1 is the gold cesium plus, you see the hump is completely vanished. Okay. Now we are detecting this kind of, if we detect any kind of signal, any kind of element in your quantum structure, then we have to detect gold cesium plus or carbon cesium plus If we grow another kind of quantum structure, say carbon nanotube, for example, then we have to detect carbon cesium plus or carbon cesium 2 plus, carbon cesium 3 plus. All these are molecules are here in the picture comes. This is a unique experiment which has been now globally very important. Now many people are now working with this, and even some companies who are working routinely the SIMS measurements, like Panasonic, for example, they are also working this alkali element based molecular SIMS by detecting the exact quantification, because quantification was impossible because of the oxidation, because of the instantaneous change in the surface chemistry, isn't it? So what happens? The CS molecule, the CS we are using incident ion is the cesium, and I know it could be rubidium, but cesium we are taking because cesium has the highest, the maximum, the bonding, the cesium bonds the maximum, the electronegativity. Let me tell you more specifically, electronegativity of cesium is very, very high for this alkali. Now the cesium when coming, this M0 is a neutral particle which is being emitted, okay, due to sputter. Now due to sputtering, the particles which are emitted, they have a very low energy. If you measure the kinetic energy, you would see something like 1, 2, 3, 4, up to about 5 eV to 6 eV, like that. If you, of course, they have a long distribution, but the maximum energy of the sputtered particles, they lie in the region from 5 to 7 or 3 to 4, like this. Now, when they are coming, this neutral particle which is being emitted, M0, when it is coming in the close proximity of cesium, okay, cesium which is re-sputtered. The cesium is incident, but is getting re-sputtered. So the cesium re-sputtered having low energy, again low energy, and the M0 neutral, the element of interest, they are coming in the close proximity. When they are coming in the close proximity, what happens? The electric field comes in the picture, because the cesium has an electric field. Electric field, it polarizes. It polarizes this M neutral atom. When it polarizes, what happens? When it polarizes, it is, there is the dipole moment. The dipole moment of the M0, because it has been polarized by the electric field of cesium. The dipole moment and the electric field, they are interacting with each other. It is a weak force. It is a van der Waals interaction. And the weak force, it's a pseudo molecule, but our experiment has to be conducted until the molecule is forming, until the formation of the molecule remains. Okay, so our experiment is done and the molecule can be dissociated. We don't worry about it. Okay, now as you can see, the electric field is E. So the polarization is proportional to the electric field, and the polarization is equal to some constant into electric field. And this is the most important parameter in my work, which is called the atomic polarizability. So the element, every individual element has an atomic polarizability. Okay, if you go to the handbook, you would see every individual atom or element has an atomic polarizability. Okay, now as the atomic polarizability is more and more, you have more chance of the formation. This we can see. The dipole moment, as I told, is interacting with the cesium electric field. So this is a molecule, the strong correlation between the MCS intensity and the atomic polarizability. And if you make a plot, you would see the more the element of, you see the lithium, potassium, calcium, sodium, they all have very high atomic polarizability, and they all have very high formation probability of MCS molecule. Is the idea clear? And so, of course, I have to skip all the kind of figures, and I should tell you that we have also done with the MCS2 molecules, and MCS2 is better because the formation probability is of course much less, but the detection sensitivity is even higher compared to the MCS. Okay, and you can see the the fluorine concentration. The fluorine concentration, you see, this is the FCS concentration as a function of depth by the Sims, and it is the FCS. I mean, F is the M, and CS is the your projectile. So FCS is you are monitoring FCS molecule, and when you monitor FCS2 molecule, you are having 3 orders of magnitude higher detection sensitivity. Okay, so when you have a low concentration of element, extremely low concentration, what is impossible to detect by the MCS, you have to go to the MCS2. But the question is now, could you be able to detect? Because the detection sensitivity is getting, you see, getting very, very difficult to detect MCS2 molecules. But the concentration, of course, the low concentration can be detected. I should quickly go to the analysis part. I would take a couple of minutes that we're now going to the quantum structure analysis. This is the first, this is a very important analysis. We're using the same machine that this is a long superlattice structure, about 160 layers, about 80 periods, silicon iron, silicon iron, silicon iron, silicon iron. So silicon iron is making a 1 pair. So silicon iron, it's an 80 period layer or 160 layered neutron mirror. Neutron has a very high penetration. So neutron cannot be reflected, So how to prepare a mirror for neutron? Naturally, you have to go kind of superlattice structure, like multi-layer deposition technique, where you have constructive interference at every layer, every pair. Then finally you are having high reflectivity. Okay, that's another part which will take long time to explain to you. But you can see this is the Sims measurement of silicon iron. Silicon iron. The red one is iron and the blue one is silicon. You can see that the profiles of iron and profiles of silicon, they are perfectly, you see, where you get the profile of silicon, you don't have the profile of iron, isn't it? Because you are having a superlattice structure. You have a thin film of iron, then you have a silicon thin film. Then you have an again thin film. So where you are having a peak of silicon, you at the same position, you can't expect a peak of silicon. When you have a peak of iron, you don't expect a peak of silicon. So you are having a periodic structure of the Sims list, and this is exactly matching the thicknesses, and the thicknesses have been measured. The total layer thickness and individual pair thickness, individual layer thickness is possible to measure because it is a measurement of the signal as a function of depth. It is impossible to measure by any other means because it's directly. People are working on the X-ray diffraction. That is, of course, the X-ray reflectivity or other or small angle X-ray diffraction. But all are indirect methods because you have to simulate the experimental results by some kind of modeling. But we are directly looking the elements. We are directly looking the elements at every point where we are expecting. This is a gold, copper, gold, copper, gold, copper interface, multi-layered structure. We have grown it, and this is a 10 bilayer structure. And you can see at every interface, there are alloys, different alloys like a copper gold, gold Cu, 2Au, Au, 2Cu. Different alloys are forming across each interface. And importantly, most importantly, these kind of alloys are spatially separated across each interface. So the machine or the instrument has to have a very high depth resolution so that they can spatially separate. We can spatially separate the individual species across interface. This is another word, but I should not tell, but we have been able to get a kind of peculiar alloy, which is called D023 structure in this kind of gold, copper, gold, copper, gold, copper multi-layer structure. I'm not going into that part, but only I will tell you that we have grown some kind of aluminium gallium arsenide, aluminium gallium arsenide, indium aluminium gallium arsenide, aluminium gallium arsenide. These are the structures. This has been, of course, the measurement has has been done in another laboratory, but this is not using my machine. But this is, you can see the quantum well. You see, this is the quantum well. So this is the quantum well, indium, aluminium, gallium arsenide. Oh, and this is, you can see the indium peak remain. The indium element is existing in the quantum well structure, because this is the lower band gap. This is a higher band gap. So this is the quantum well. So the indium concentration you are detecting when you do the SIMS. So the concentration as a function of dynamic SIMS. This is not static SIMS, because you are eroding and eroding and eroding. You are doing depth profiling. You are getting indium concentration at the interface of aluminium gallium arsenide and indium gallium arsenide. And you can eventually get the indium distribution. If the indium interdiffuses into the aluminium gallium arsenide, you can measure the interdiffusion of indium across the interfaces. So you can imagine interface is never short. When you grow thin film or a quantum well, interface has to be ideally very sharp. But because of interdiffusion, interface is always makes a fuzzy structure. Interface gets a broadened structure. This is a multiple quantum well structure, and gallium arsenide, aluminium gallium arsenide. This is SIMS measurement of aluminium. Aluminium is located into the quantum well. So this is aluminium concentrations. As you can see, quantum well is the signature gives you the quantum well distribution. What are this is the sphere. The circles are giving the measured values, and the dotted the solid line is giving the MRI calculation, MRI convoluted things. It is the because there is a mixing at the interface. We are taking a mixing up to nanometer. We are taking a mixing surface roughness, because surface has a roughness. It's the root mean square roughness. It's about 1 nanometer. And information depth, how much information depth we are talking about. So if we take in the W atomic mixing, surface roughness, and the interface and the information depth, we are getting a beautiful match of the SIMS profile. Okay. The work has been presented, is being published in a book of Handbook of Material Science, Volume 1, Optical Materials, which is coming within a month, which is published by Springer Nature. Of course, I must tell you there are 2 more publications which are coming. One is another Springer Nature, another is International Journal of Modern Physics B. So I'm not going into the details of those publications. I think, how much time I should have? Can I
5 minutes more is remaining,
okay,
sir.
Okay, thank you so much. Thank you so much. This is a silicon germanium multi-layer structure. This is important because we have been able to do X-ray reflectivity. Okay, and X-ray reflectivity, we had a strong group in our laboratory who had been routinely working on the X-ray reflectivity by using our laboratory X-ray machine, or using synchrotron of Japan, synchrotron of synchrotron of Italy, and synchrotron of other things. For example, DESI synchrotron in Germany. And so so this is the measurement what has been done. This is done in the DESI lab, and this blue one is the electron density profile, which has been extracted from the X-ray reflectivity. From the X-ray reflectivity, one can extract the electron density. And electron density profile should match with the actual concentrations. If you do by SIMS, you see the red one is the SIMS measurement. Remember one thing, we are doing MCS. We are not doing SIMS. We are doing molecular SIMS. We are doing the alkali element. Cesium is alkali. So we are doing alkali, because I told you a number of times that we are using alkali metal based molecular SIMS, because this gives us the exact quantification. The quantification was impossible in the normal SIMS because of matrix effect. So that was a stumbling block in the entire scientific community, how to minimize the matrix effect. There are many examples. There are many standard procedures by ion implantation, by creating standards using ion implanted material. People have done, and using the high energy ion the high energy ion, high secondary ion energy distribution, that part, if you detect the very high part of energy distributions, of course, that is possible. They are not suffering the matrix effect. Very idea is very clear, because the high intensity part of secondary ions, they are very quickly apart from the top surface, because they're very high energy, isn't it? So they are not looking the surface chemistry anymore. So because you are not allowing them to remain in the surface vicinity, isn't it? So basically, that's all our procedures are there. And I have not talked about another, that's the highly charged ion-based SIMS. That because of the time constraint, I could not go into that. That was very interesting part I have missed in my talk today. That was a very high interesting part, that if you do highly charged molecular ions, where you have almost all electrons of an atom have been stripped off, okay? For example, you are taking an atom which is coming on as a soft landing on the surface, but the atom, not atom, but it is almost a hollow atom. Hollow atom means every electron has been stripped off. So all energy states are vacant. Now what will happen? You can imagine when they are coming in the close proximity of the top surface, what will happen? The electrons in the conduction band, they will try to quickly jump to the valency, those energy states which were remaining vacant in the hollow atom. So there are a lot of atoms will quickly jump to the energy states. Okay, so immediately there will be a lot of positive ions accumulated on the top surface. They are clustered together, the positive ions, because the electrons have been ejected due to they have taken the vacancy states of the hollow atom. Now, because of the positive ions are all flocked around, they are all clustered together. What will happen? You can imagine there will be a big Coulomb repulsion. Because the Coulomb repulsion, all the positive ions are coming out, ejection is happening. So we are now measuring those positive ions by the SIMS process. Is the idea clear? Now that SIMS is not seeing any matrix effect. That SIMS is not looking any kind of surface oxidation or any instantaneous surface chemistry. That is another important part of my talk. I have not gone to that. And of course, that was a very interesting talk, because interesting part, but with that technique, one can grow nanostructures also. By using the highly charged ions, one can really grow pattern structure and do the SIMS also. Okay, now you can see the SIMS measurement of this kind of silicon germanium multilayer. They are matching exactly, so that at the same every layer you are getting the thicknesses. Okay. Of course, the intensity would be different because it is electron densities and this is the atomic concentrations. They cannot be exactly equal. So there are some kind of limitations in, for example, there could be some kind of segregation or interdiffusion. So those things are possible, you know. So I should take 2 minutes more, and then as you can see, this is no, this is not important now at the moment, but this is, you can see MCS2 is better, because you see the ionization to the molecular formation, the intensity are very are exactly linearly proportional, linearly dependent on the concentration ratios. So the germanium silicon, if you have a, for example, if we grow alloy. Now we have done it, of course. We have grown alloy structure by the MBE, and where the silicon actually having low concentration of germanium, maybe 0.1. So silicon could be, germanium could be 0.1 and silicon could be 0.9, or germanium could be 0.01, etc. Or silicon could be, sorry, for example, 0.99, something like that. So depending on the different concentrations of germanium, alloy formation, alloy structure, alloy composition could be different. Now for all alloy compositions, you see, if you do measurement of germanium, cesium, silicon concentration ratios from the energy dispersive X-ray analysis, this is from the energy dispersive EDX. And if you do the SIMS measurement of MCS, germanium cesium divided by silicon cesium, you see they are exactly matching. So it is MCS, it was not exactly 45 degrees, but for the MCS2 molecules, they're exactly 45 degrees. So it exactly matches. So the concentration ratios from the intensity ratios of MCS2 molecules of germanium and silicon, you can directly extract the concentration ratios in an alloy of germanium silicon. This is our work, which has been published in a couple of journals, and this is a it has a high citations of this, because nobody has done this kind of measurement by the molecular SIMS. And okay, finally, I would tell you that photonic material, which is called the metamaterial, is important for the SIMS. Metamaterial is a material where it's similar like superlative structure, but ideally the materials can contain, for example, some kind of metals and some kind of plastics, some kind of ceramics and metals, and these are kind of superlative structure and having different, thicknesses and all. And if you grow, material is grown by the MBE, of course, and then if the light comes here, the light is bending in an opposite direction, the negative direction. So the light is not refracted as the normal refraction is. So it is called the negative refractive index material. So we are now working on photonic metamaterials. My recent article on the photonics has talked a lot about the photonic metamaterials. So actually, I have talked a lot about these metamaterials in this chapter. So there you can see, as the light is shifted, the light is coming that way and it is being shifted. This is one kind of superlative structure. This is another material superlative structure. So they are repeated. The light is refracted, but in the other direction. And from the shift of the light, this is the normal position, and this is the shift. From the shift delta, one can estimate the refractive index in the negative direction. I think I should stop here, but before going to that, I would give you one or two slides of the imaging by the SIMS, and you can see this is the titanium nitride spider image on silicon done by the SIMS in our instrument. And this is of course, for that we have to couple another part called the focused ion beam setup, focused ion beam microscope. This is already coupled with our instrument, and this is giving the optimum ion collection. And we are getting an aluminum image. The red dots are aluminum image concentration. You can see concentration distribution on the grain boundaries of lanthanum, strontium, copper, iron oxide. So this is superconductive element, but aluminum can be distributed, and by the SIMS imaging, one can see directly the image of aluminum by the SIMS imaging, of course. And this is, you can compare secondary electron image and secondary ion image by the SIMS using the focused ion beam microscope. As you can see, this is much better resolution once we do the secondary ion microscope. And this is a SIMS image of a 200 mesh copper grid structure. This is a grid structure, 100 micron holes and 30 micron bars. And this is a structure using gallium beam. I should tell you, this is done with a gallium liquid metal ion source, because gallium is in the molten state in the room temperature. So from the ion source, it is already in the molten state. So this is done with a liquid metal ion source. And finally, I have to stop here, thanking all of you for your patient hearing. Thank you so much.
Thank you so much, Professor Purushottam, for this astounding presentation. I mean, it's so exciting to see, and hats off to your unparalleled zeal and energy by which you just presented this whole topic. And I would have loved to be a student of the basics of the quantum physics that you discussed about, and the SIMS and molecular SIMS instrumentation and everything. I mean, thank you so much for this whole thing.
Thank you.
I'm sure all the viewers must be very curious about the whole science that you have been doing and you are doing right now. But we are unfortunately running ahead of the time, and we are 10 minutes already past.
Yeah. Okay.
I would just ask once if somebody is having any burning question with them, and then we can take maybe one, or else we will go on with the next presentation. Anybody from the audience? Okay. If not, then thank you very much again for joining us in this conference, and yeah, I would like to definitely come back to you with my questions maybe later in this session. Thank you so much.
My pleasure.
So we will go on with the next presentation. Our next speaker is Professor R.K. Pendinti. He is the HOD of Department of Chemistry in IIT Roorkee. Let me give a brief introduction. He obtained his MSc and doctorate, doctoral degree from University of Hyderabad under Professor Basavaya, by working in the area of enzymatic enantioselective synthesis. Later, he moved to Germany as a Humboldt Fellow, and again to Taiwan. And then he took the faculty position in IIT Roorkee in 2004, where his main focus of the research area is towards development of simple and facile strategies for synthesis of molecular frameworks with complexity, and also of biological and pharmaceutical relevance. So thank you, Professor Pendinti, for joining us. And now the floor is yours.
Yeah, thank you, Chairperson, Dr. Sritama Mukherjee. Can you hear me?
Yes, I can hear you.
Yeah, thank you. Just I'm trying to share my slides. Can you, I hope it is shared now.
Yes, we can see the full screen.
Thank you. At the outset, I would like to thank the organizers of the event, editors of Science Dialectica, especially Professor Arup Kumar Das, for giving me chance to present some of our work in this august audience. Yeah, so the topic is like development of new catalytic reactions at this today. And I acknowledge all my laboratory research group members, IIT Roorkee, and all the facilities, financial support from different funding agencies, my collaborators, and also web resources and scientific literature for some of the images I have taken for this presentation. Yeah, some of the aspects of the green chemistry are catalysis, solvent replacement from hazardous solvents to non-hazardous solvents, and use of renewable feedstocks, waste minimization, and also energy efficiency, separation process, and other things which we can minimize the waste and also reduce the use of energy. So catalysis is one of the key components to promote the reactions. So some of the green protocols generally we come across are solvent-free reactions. Generally we perform organic reactions in some of the solvents, organic solvents. So if there is a possibility to carry out these reactions in solventless conditions, that is one of the good opportunities for green protocols. And also we can replace organic solvents with water to perform the reactions in aqueous medium. And also we can try the catalyst-free reactions if it is possible. Atom economy is one of the important aspects of the green protocols. And also if you can perform the reaction in a faster, rapid manner, so we can perform multi-batch reactions in short time, which is useful for the industry. And if possible, we can also reduce the solvent separations I will show some of the solvent, some of the aspects of purification of compounds after completing the reaction. And if we can avoid purification steps like column chromatography, simply by if your product is like solid, then you can think of simply filtration. If you can get better purity of the compound, and reactions we can think of in quantitative yield, means nearly 100% chemical yield is possible, then those reactions can be promoted. So some of the things, if you see our old literature or our Indian culture, you can see, you can think of having simple grinding. You take the substances like reactant 1 and reactant 2, you can grind in mortar and pestle. So if the reaction completes, then it's a good possibility. And you can think of you can think of grinding reaction mixture, and if reaction completes and gets a final compound, that's good. And some of the things we have carried out is, for example, for any reaction to get instantaneous reaction or fast reaction, the electronics of the reactant substances is most important. Electronics in the sense, one component should be highly electron rich and other component should be highly electron poor. Then such type of combination of such type of reactants can undergo reaction in a facile manner. So one of the some of the electron rich materials are amine functionalities and also sulfur compounds. And these electron rich material can undergo reaction with electron deficient materials like, we have groups like nitro group and also electron withdrawing groups like carbonyls and ester functionalities and halogenated substrates. They undergo, they show the effect of electron withdrawing nature. So in the process, the entire molecule will become electron deficient. So then electron rich component can attack on the electron poor component to make a new bond. Either it is a CC bond, carbon-carbon or carbon-hetero bond. So in this case, amines and beta nitrostyrenes we call. AR stands for aryl moiety, like phenyl, that is benzene moiety, and other aromatic systems. So here, whenever you take these two things in a petri dish, and within few minutes, after mixing of few minutes, we can get the product. And here, the reaction is addition reaction. So wherever we have addition reactions, there won't be any byproducts. So addition reaction, there is no byproduct. Once the complete conversion, that means if your reactant A and reactant B, if they involve in the reaction completely, then you will get the complete conversion of the product, and there won't be any side products because it's addition reaction, and we can get a pure compound. That means pure product. So similarly, we have carried out some reactions. These are known as orthoaminothiols or phenols. Such compounds, again, they are having electron-rich character or amines. And we have other triple bond compounds like acetylenic compounds having electron withdrawing groups like ester moiety. They are electron deficient species. So therefore, we can expect a facile reaction between these two types of reactants. So amino alcohol, that is amine functionality, and also OH hydroxy functionality on the benzene ring. They are orthoaminophenols. So they undergo addition reaction with acetylene dicarboxylate. So here the byproduct is if you take COOR as COOMe, that is methyl ester. So byproduct would be methanol. Methanol is a volatile substance and it is very easy to remove from the reaction mixture. So therefore, here the product is this one, also known as benzoquinone mono. This is like benzoxinone derivatives, and byproduct is methanol. So methanol is easy to separate. So therefore, we can easily separate the product from the reaction mixture. So we can have different types of substrates, and with the R1 here means different substitutions on the benzene ring. So we can have a product yield of 100%, that is quantitative yield we call. So it is complete conversion. We can get within minutes, let us say 1 to 3 minutes or 5 minutes, we can get complete conversion to the product, and also yield is quantitative yield. So this is another reaction. It is known as the Diels-Alder reaction. That is, we have diene. Diene means now we have two double bonds in a conjugate manner. That is double bond, single bond, and double bond. We call 1,3-diene system. And also we have one single bond, that is C double bond C, that is known as dienophile. Means we call this one as 2-pi component, and first one is known as 4-pi components, because 4 pi electrons are involved. Each pi bond has 2 electrons, so therefore 4-pi component and 2-pi component. The reaction between these two gives a cyclic system, and it is again addition reaction. So therefore we can expect no byproducts, only product, the final product can be obtained. And if the reaction is complete, no starting compounds will be remaining in the system. Therefore, we can expect 100% chemical yield. So yeah, why there is a necessity of catalyst here? Here, we are choosing our components or substances in such a way that they have very good electron match. Means one has a highly rich component in electronic sense, and the other one is electron poor substance. Therefore, we can expect a better interaction, thereby formation of a new bond to get the final product. So all compounds cannot undergo at room temperature under this type of thing. So therefore, yeah, these are some of the examples. Yeah. So why the catalyst is required, and what is the role of the catalyst? So we know that for any reaction to undergo, we need to cross the barrier of activation energy. That means in case if you have A and B, two components, so in order to reaction to occur between those two, it has to reach the transition state. The energy of activation is required for the successful collision of these two components. So therefore, to activate this reaction, so we need to cross the energy barrier. So sometimes energy barrier will be very high, so therefore we have to provide more energy. So the catalyst here, it helps to reduce the activation energy or activation barrier. So therefore we can perform the reaction at lower temperature. So in the absence of catalyst, we have to supply more energy. But once if you have the catalyst, so we can easily cross the barrier, because the activation energy barrier will be going down with the help of the catalyst. So for example, if you see here, so the one which is in red color is the activation energy for the reaction without any catalyst. So that means this is uncatalyzed reaction. The activation energy is this much, and if you use some sort of catalyst, so the reaction will be catalyzed with the help of catalyst. The activation energy barrier will come down. That means we can perform the reaction at a lower energy. So therefore, catalyst will bring the activation energy to a lower level, so that reaction can be easily performed. Also, if you see some catalysts, we have this type of surfaces. So the catalyst itself is in the form of surface. So both the reactants like A and B will be bound to the catalyst. Therefore, these two, for example, hydrogenation case, we have hydrogen as the gas. So the gas will be binding to this catalyst surface. So the reactants will be brought together with the help of the catalyst, and therefore the reaction will be occurred because of the proximity of these two reactants. So engines are also they are biocatalysts. So engines are very selective. They also have better selectivity, not only simple selectivity, but also enhanced selectivity will be possible. That means any two out of two possible engines can use selectively only one product. So engines, what they do is they there is a lock and key system. So that means there is a cavity in enzyme. So the substrate will fit into the cavity. Then the two substrates will come closer within the cavity. Then the reaction will be proceeding. So therefore we can get the product. So we can also think the catalysis in a different way. So for any reaction, no, if you have two components, for example, two substrates, so reactant one will be having, yeah, without going to that, I can say that, no, if you see like atomic orbitals will be having the same way, we also can have molecular orbitals. So some will be filled with electrons, some will be empty orbitals. The filled ones will be having several filled orbitals. So the one which is having highest occupied molecular orbital, among the filled orbitals, the one which is having highest energy, that will interact with another molecular orbital of other reactant, which is empty in the sense. So this is known as lowest unoccupied molecular orbital. So this orbital is of another reactant, which is empty, but it is having the lowest energy. So therefore, between these two, so the energy gap is minimum. So HOMO of this NU stands for nucleophile, that means electron-rich species. E stands for the electrophile, electron-deficient species. So the energy difference between these two orbitals, one is of nucleophile, other one is of electrophile. So the interaction, if it is successful, we can get the product. But if the energy gap is more, then reaction is not possible. So in that case, we can use catalyst. It will activate one of the components, in this case electrophile. Then it reduces its Lumos energy. So then we can see the energy gap between HOMO of nucleophile and LUMO of electrophile in the presence of the catalyst. It came down drastically. Then we have better interaction, so then reaction will be facile. So by using catalyst, the energy gap between HOMO and LUMO can be reduced and we can proceed for the reaction. So for any interaction, for any bond formation, the interaction between HOMO and LUMO of these two components is essential to make a new bond. So just I'll go quickly how we do reactions in the organic laboratory. So we perform reaction in the RB flask, for example, with magnetic bead or pellet we call, and stirrer will be there, magnetic stirrer. So we can also perform reaction with the help of condenser. If you want to reflex the reaction to attain more temperature, we can use it by circulating water in the condenser. Otherwise, we can perform the reaction at room temperature without heating. So if you look like this, also we can perform reactions under inert atmosphere like nitrogen gas or argon gas by using appropriate arrangements. We monitor the reaction with the help of thin layer chromatography, it is known as TLC. What we do is we keep the spot of the reactants. Here we have two reactants here. One is beta methyl, other one is this butyl tosylate. The reaction between these two will give us the product, this one. This is one ether. So what we do is at 0 minutes at the beginning, start of the reaction, we can see the two spots. These two spots are nothing but one is of one reactant, other one is other reactant. As the time passes, so we can see a new spot arising here. So the new spot is belonging to the it is of product. So yeah, after some time, and these two substrates are supposed to disappear. But sometimes we take slight excess of one of the reagents. So in that case, the excess reagent will be still in the reaction mixture. Otherwise, we can see the product. So in real sense, it looks like this. We take TLC plate. It is actually stationary phase is silica gel or alumina, and we take mobile phase solvent to move the these compounds or spots. The movement will depending upon the polarity of the substances and also the solvent system. So yeah, we can get we can monitor the reaction based on the time. Once if the substrates are completely disappear, that means the reaction is completed. So afterwards we call workup. We take the material in separating funnel, we shake it. If you have any acidic catalyst, we use neutralize with base or basic catalyst, then we can neutralize with acid. Then you can separate the two layers. One is aqueous layer, other is organic layer. Your organic compound will be solved in organic solvent, so therefore we can see the product, organic product in the organic layer if it is not a salt. So then we can separate the two layers and take the organic layer and remove the solvent with the help of rotary operator. So then we can get the residue, that is product plus some impurities, if at all. That one we had to separate by column chromatography. It is a gravity-based chromatography. So what we do is we have stationary phase, mostly silica gel, and we afterwards we use our residue, the product reaction mixture which we received. We got it after the reaction workup. Then slowly we pass the solvent system, that is station mobile phase. We collect different fractions based on the, like, we may have more than one compound here, so all the fractions we can separately collect. So each one fraction belongs to one individual component, that is different product. So then we can characterize based on IR, proton NMR, carbon 13, and also 2D NMR if required, and also mass spectrometry, and also single crystal X-ray analysis. Yeah. So we have we have used different reactions. In this case, we used iodine as a catalyst. So the reaction is very fast. Within 1 minute, the reaction completed. And another important thing is there is no need of any column chromatography here. Simply by taking the material and extraction and separate 2 layers and get the product. So yeah, yields are very pretty good. And actually, the important point here is to have a faster reaction rate, we have to select our materials. With a good electronic matching. Otherwise, also, if the reaction is not possible in the absence of catalyst, then we have to activate the substances with the help of catalyst. So catalyst, generally we use Lewis acids and bronzite acids and also organic bases based on the requirement of the reaction and also nature of the substances. So for example, in the earlier case, we have obtained this compound within few minutes. Then these products, now they can be used as substrates or precursors for further reactions. So these benzoxenones, they are they have one type of arrangement known as enamine, that is olefin, and also amine, that is nitrogen material. So therefore, it's known as enamine. These enamines are very good nucleophiles, means electron donors. So then electron acceptor here, nitrostyrene. So there is a reaction between these two. Initially, the addition of this enamine takes at this carbon, we call benzylic carbon, this one, then followed by cyclization. The driving force for the cyclization is here. If you see carefully, here we have 5-membered ring with nitrogen. It is known as pyrrole. This pyrrole unit is aromatic. So any product formation with the aromaticity, that will give the stability to the product. So therefore, the reaction will be proceeding in this direction. So generally what we do is we take different types of substituents on the substrates. Different, for example, in this case we have AR stands for aryl. So different aryl groups, that is naphthyl, and also phenyl ring with paramethyl groups and also dimethoxy groups, halogen attached phenyl rings. So all the substituents, they are also giving reasonably good yields. So here also we use different groups in the left side of this ring. Like methyl ester. Methyl is electron releasing group and ester group is electron withdrawing group. In all cases, the reaction proceeded to give the corresponding products. So the activation of the reaction, here we use trifluoroacetic acid. Trifluoroacetic acid, the H plus of this trifluoroacetic acid, it binds to the carbonyl group of this ester. So then, due to the binding of this one, electron flow will be towards this direction. Then the lone pair on nitrogen will be moving towards this, and it will activate the entire molecule to make this one better nucleophile. That means electron donating material. So therefore, the electron donation will be taking place and to attack on the beta carbon of that is beta nitrostyrene, we call. So once if it is initial attack happens, then CC bond will be formed. Then there will be cyclization, another CC bond or here NC bond formation. So then followed by removal of these groups to give another double bond to become a aromatic structure, aromatic moiety within these molecules.
Just to specify, you have 5 more minutes left.
Good, fine.
Yeah.
So we have done different types of reactions. So this is the different electrophiles we use here with the same substrates. And all cases we have better yields, and also the reaction is having same mechanism here also. So another important thing is we can reduce this carbonyl group to give corresponding OH with reducing agent sodium borohydrate. We can get this type of OH, which is similar to the aromatic carbon of the carbohydrates like sugar, for example, glucose. Okay, here these are the products of after reduction. Yeah, here we use sodium methoxide to open this thing and to give this type of butyl. All these molecules are useful in the medicinal thing because heterocyclic systems are very much useful. What we do is we synthesize these compounds and we go for the biological activity studies in the neighboring biotech department. So these are another nucleophiles with nitrogen containing system with 5-member rings. And also we can use FeCl3 as another catalyst for this type of reaction. Okay, these are the examples in this reaction. And always we use, of course, DC stands for dichloroethane, that is solvent system here. And we have other different types of electron withdrawing group, we call electrophile, and also actually this already in this, if you see, we have 2 rings here and also 2 rings, total 4 rings, and we can also have cyclization with the appropriate system. So we can get polycyclic systems here, which are very much useful in the medicinal chemistry. Okay, these are the examples here. Sorry, I go quickly. So just I want to give a flavor how things go on in organic synthesis lab. Okay, these are other type of electrophiles. So here the product is this one, and here we have at the end of the reaction there is a aromaticity, there is a driving force for the reaction. Okay, and these are known as para-benzoquinone methydes, monomethydes, and these are the electrophiles. Okay, these are the other types of systems. Here this is the electron deficient species, and this one we can make as electron rich to have bond between these two to give polycyclic system. Okay, just I'm going towards end. Okay, yeah. Again, this is another system which is nucleophilic system to give pyrrolocoumarin type of heterocyclic systems. Yeah, this is the summary. We can get the products from the simple method, and also we can use them as precursors for further elaboration of the reactions. So I thank for your kind attention.
Thank you, Professor Pendinti, for this wonderful presentation where I could really see the vast number of organic reactions and products that you have already achieved, and of course it talked about the green protocols and how you simplified the organic reactions by following the green chemistry parameters, and still you could maximize the yield of the organic reactions. That's wonderful. So anybody is having any questions? We still have probably a couple of minutes if anyone wants to ask. If not, so you just said that these molecules that you have synthesized, they are being tested or in the biotech department. So, like what? Like I am curious to know what kind of applications or the usage of these kind of organic molecules have have you already seen something?
Yeah. So actually, everything depends upon the nature of the moiety. So for some sort of moieties, they are useful for the anti-cancerous activity. Some are microbial like that. So some of our products, they have shown a very good anti-cancerous activity. So that is now they are trying for collaboration with industry for further work actually. And also some products have antimicrobial activity. So generally what we do is we give the synthesized products, and also we go for the SAR studies, structure activity relation. For that, what we do is we generate a library of products. So based on the requirement of the other group. Yeah.
Okay. Yeah. So, just for my curiosity, so these molecules which you see, the anti-cancerous and this kind of utility. So, how much do you think is, from the lab scale that you saw some such activity, and from it, from there, the molecule to go to the industry, how is the process, or have you witnessed anything where the molecules actually being tested by the industries or the pharma to see that if they can be really of some use?
It's not gone to that level, because there are so many levels will be there,
So many,
and
exactly.
all molecules cannot be going to the
Yeah.
panel level. So many thousands of compounds they test all over the world. So yeah, it's only they want to have further testing. That's all.
That's thank you for this wonderful presentation. It was really very interesting to see. I think we have one more question for you. So from Raneev Thakur. So the question goes like, how green chemistry will be helpful in formulation of nanoparticles?
Yeah, green chemistry, actually, we have 12 principles in green chemistry. Hopefully, our next speaker will be working on, giving talk on that. So it's very difficult to have all 12 points to, make satisfaction, because some of them we can go, if it is, if you, satisfy all the 12 points, then it will become absolute green synthesis. So,
Right.
yeah. So, the only thing is we have to, wherever there is a possibility, we can replace solvents with hazardous solvents with non-hazardous or less hazardous solvents. For example, chloroform can be replaced with some other solvent like, dichloroethane, etc. So then certainly, they will be useful. But only thing is we have to see if you can perform reactions instead of organic solvents. If you replace it with water, for example, aqueous medium, that is another, we can overcome in that way.
Right.
Certainly, we can use it.
Sure. Yeah. Thank you so much for the presentation. We can now move on to our next speaker. But before doing that, probably I will make an announcement for the young audience that we have with us. So please go through the presentations quite attentively, because you will be having your quiz session after all the talks gets over in this session, and in that quiz you can have a variety of questions, basic questions related to the presentations, and also the quiz, the winners of the quiz will be having will be getting some goodies. I hope so. Moving on to the next talk, we have Professor Venkata Krishnan from IIT Mandi with us. Let me give a brief introduction of him. He completed his PhD in chemistry in 2006 from University of Stuttgart, Germany. And then he worked as a postdoctoral researcher in University of Pennsylvania, and followed by his position in National Institute of Material Science, Japan. And then he joined as a faculty in IIT Mandi in 2012. And currently he is a full professor. He has published more than 180 articles in well-reputed international journals and is also a reviewer for several scientific journals. He has been bestowed with several awards, including DST Inspire Faculty Award, IIT Mandi Foundation Day Award for Excellence in Teaching, a MANA Research Fellowship, DOE Postdoctoral Fellowship, DFG, and DARD Visiting Scholar Fellowships. So I'm looking forward to your presentation. And the floor is all yours.
Yeah, thank you. Thank you very much for the kind introduction, and thanks a lot to Professor Arup Das for kindly inviting me for giving a presentation to this August gathering in this conference. Let me share my screen and then start my presentation. Is my screen visible now?
Yes, yet to go to the full screen mode. Yeah.
Okay, is it now in full screen mode?
Yes.
Great, yeah. Thank you once again to the conference organizers, and also to my previous speaker, Professor Pedinti, because he has already touched upon several aspects which I'm going to speak about in my talk. So I'll be talking about green chemistry and heterogeneous catalysis for energy and environment applications. So since I was already introduced, I'm not going into my academic background. And for those of you who are wondering where IIT Mandi is located, so IIT Mandi is located in the center of Himachal Pradesh in a city called Mandi. And it was established in 2009, and it currently has about 2,800 students, around 200 faculty members, and about 250 staff members. And these are some photographs of our campus. So our campus is divided in two. This is called as the South Campus, and this is the North Campus. And these are some of the buildings in our campus, and this is where one of our lab is located. So it's a very beautiful place our campus is located. And this is my research group. So first and foremost, I would like to acknowledge all the members of my research group, because they are the people who have done all the works, and I'm in front of you presenting their research works. And especially in today's talk, I'll be talking about the research works done by three of my former PhD scholars, Dr. Tripti Chabra, Dr. Priyanka Chaudhary, and Dr. Ashish Kumar. So our group is actively working in the field of heterogeneous catalysis for energy and environment applications. And within this domain, we work in the field of biomass conversion, organic transformation, carbon dioxide reduction. These three things we do it thermocatalytically. And apart from this, we also work in the domain of hydrogen evolution, pollutant degradation, and nitrogen fixation. These three we do it photocatalytically. So overall, our goal is to develop a novel heterogeneous catalyst which can be used for energy and environment applications. So now here comes the question, why there is a need for sustainable development and why it's now. When we look at the conventional approaches employ expensive metal-based catalyst, high temperature and high pressure conditions, and also involves the use of harmful solvents, including certain toxic reagent, and the entire process is quite difficult to handle. On the other hand, when we look at the sustainable approach, we can use metal-free or inexpensive catalyst for doing the same type of reactions. We can use mild reaction conditions like low temperature and atmospheric pressure conditions. We can also use environmentally benign solvent, as my previous speaker touched upon. We can use the environmentally benign solvents, and thereby we can reduce the waste and have less detrimental impact on the environment. So how we achieve in our group, because our group is extensively working in the field of heterogeneous catalysis, wherein we design certain catalysts and use them for the particular application. So we are imposing certain design constraints during the process itself. So some of the design constraints that we use are use of earth-abundant elements, predominantly metal-free and low-cost materials for developing the catalyst, use of non-toxic and non-polluting chemicals and processes, use of relatively low temperature, that is less than 250 150 degrees for the catalytic reaction, use of ambient pressure, that's about 1 atmospheric pressure for the catalytic reaction, and adherence to the green chemistry principles. So all the 12 green chemistry principles to the best extent possible. And finally, to catering to the relevant UN Sustainable Development Goals, we'll see what are the goals which we are trying to cater to. So these are the 12 green chemistry principles my previous speaker already touched upon. So we are trying to come as far as possible adhere to all the 12 green chemistry principles. So this can be found in any textbooks on the green chemistry. And there are totally 17 sustainable development goals postulated by the United Nations. And we are kind of working on 5 important goals, which are the clean water and sanitation, affordable and clean energy, responsible consumption and production, climate action, and finally, partnership for the goals. And now moving on to the main material which we use as the catalyst, we are using this material, which is the graphitic carbon nitride material as the catalyst. And as you can see, the graphitic carbon nitride, this material consists of carbon and nitrogen atoms, both of which are earth abundant atom, and they are arranged in a form of a graphite sheet. That's why it's called as the graphitic carbon nitride. So the pattern in which it's arranged is the Spris triazine based pattern, as it is shown here in this figure. And this material, the graphitic carbon nitride material, can be easily synthesized by polymerization reaction of any of these precursors, which include cyanamide, dicyandiamide, melamine, or urea. And the formed graphitic carbon nitride is highly stable both chemically as well as thermally, which means that if it reacts with any chemical, it doesn't easily react with that chemical. So it's chemically stable. And also it is quite stable thermally until about 450 degrees centigrade, it's stable. And furthermore, this material, the graphitic carbon nitride, is amenable for surface functionalization and doping, and which can impart a certain characteristic properties on the graphitic carbon nitride. So we can functionalize this graphitic carbon nitride using sulfonyl functional groups or phosphate or nitrate functional groups, or even we can dope this material with some heteroatoms which can take place of the carbon or the nitrogen. For example, boron could be one such example. So we can do a lot of customization on the graphitic carbon nitride and tune its properties. And in the first work, I would like to talk about the research work done by my former PhD scholar, Tripti Chopra, which is on biomass valorization. So in this case, we have converted the saccharides to 5-HMF. 5-HMF is this 5-hydroxymethylfurfural. This is a very important platform chemical which can be obtained from some biomass-based resources such as saccharides. And we have done it in green solvents. So this one, the sulfonated graphitic carbon nitride, this material has been used as the catalyst here, which possesses both Bronsted base as well as the Bronsted acid sites. So the Bronsted base sites are coming from the nitrogen moieties which are present already in the graphitic carbon nitride, and the sulfonyl group which are kind of functionalized onto this material that imparts the Bronsted acid sites to this material. And we have done experiments with many different saccharides, which includes the monosaccharides, which are the glucose and fructose, and also the higher saccharides, which include cellulose, sucrose, and starch. And all of these are converted to a highly selective product, which is the 5-HMF. And we have done these reactions with different green solvents ranging from water, ethanol, isopropyl alcohol, and also dimethyl carbonate. And finally, the synthesized 5-HMF was converted to other value-added products such as 2,5-bis hydroxymethylfuran, 5-chloromethylfurfuran, and also 5-bromomethylfurfuran. And for any material, when we do the synthesis, we need to see whether the synthesis of the catalyst is successful or not, for which we need to do the X-ray diffraction characterization, which indicates what type of structure is formed in the catalyst. And also we did the Raman spectroscopic and FTIR spectroscopic studies in order to understand what are the functional groups which are present on the catalyst and how they interact with each other. Then we also did the thermogravimetric analysis, which indicated that the material, the graphitic carbon nitride material, which is the parent material, is quite thermally stable to about 500 degrees centigrade. On the other hand, even the sulfonated graphitic carbon nitride is also quite stable to about 400 degrees centigrade, although we have used much lower temperature for our actual catalytic process. Subsequently, we need to know what is the morphology of the sample. So for which we did the SEM and the TEM analysis technique, which both of which indicated a sheet type of morphology for our sample, which is a two-dimensional morphology for the sample. And we also did the elemental mapping and EDAX analysis in order to understand what are the elements present in the sample and how the different elements are distributed across the sample. Then we did the XPS analysis on our sample, and XPS stands for the X-ray photoelectron spectroscopy. And from this analysis, we can get to know what is the oxidation state of each element present in the sample and how the different elements in the sample are interacting with each other. Furthermore, since XPS is a surface sensitive technique, it can provide information about what is the atomic percentage of the different element on the surface, and from which we can clearly see that the sulfur group which is present on the surface is about 3.27, because this is one of the catalytic active sites in the sample. Subsequently, we used this material, the sulfonated graphitic carbon nitride, as the catalyst for this conversion, wherein we have converted the saccharides to the value-added product, which is the 5-HMF, wherein the starch gets converted initially to glucose and fructose, which eventually gets converted to the 5-HMF. We also did a detailed optimization of the reaction, wherein we optimized the catalyst amount and found 10 milligram of the catalyst is the best optimal amount for the reaction. We also optimized the temperature and found 200 degrees C is the optimal temperature. We optimized the time of the reaction and we found 5 hours is the optimal time for the reaction. And finally, we also did it with the various saccharides, ranging from the monosaccharides, which are the glucose and fructose, and also the other saccharides such as cellulose, sucrose, and starch. We also did the reaction under different green solvents. We did not use any non-green solvent in our case. All the solvents used are green, so which include water, ethanol, isopropyl alcohol, and dimethyl carbonate. And we found that water gave the best result both for the monosaccharides as well as for the higher saccharides. Subsequently, we did the recyclability studies, wherein the catalyst was recycled for 5 cycles. So every time we take out the catalyst, we wash it and then again redo the reaction. And we found that the catalyst could be recycled for several cycles, and with slight decrease in the yield of the product. We also kind of determined the green matrix parameters, which include the environmental factor, mass intensity, process mass intensity, solvent intensity, atom economy, reaction mass efficiency, mass productivity, and also the carbon economy. And we obtained relatively good values for each of these parameters for the various saccharides, which indicates that our processes are green in nature. Then the obtained 5-HMF was converted to other more value-added products such as 2,5-bis-hydroxymethylfuran, 5-chloromethylfurfural, and 5-bromomethylfurfural in relatively decent yields using normal processes. And this work was published in the journal called Green Chemistry in year 2019 with my former PhD scholar, Dr. Tripti Chabra, as the first author. And subsequent to this work, we also published another work in the journal Carbon, wherein we have used a dual functionalized catalyst, wherein we have functionalized this graphitic carbon nitride with the Lewis acid site as well as a Bronsted acid site. Basically, the Lewis acid site is brought about by doping this graphitic carbon nitride with boron atoms, and also the Bronsted acid site was brought in by the sulfonyl functional group present on the graphitic carbon nitride. And we have used it for the conversion of monosaccharides to 5-HMF. And subsequently, we have done another work wherein we have used the acid functionalized hydrochar. And in this case, the hydrochar was obtained from waste orange peels. And we have functionalized it with 3 acids, so like sulfonic acid, nitrate, and also phosphate. These 3 are acidic moieties which are present on this material, which is the hydrochar. And we have used this acid functionalized hydrochar as a heterogeneous catalyst for the solventless synthesis of biofuel precursors. And this work was also published in the Green Chemistry Journal in 2022 with my former PhD scholar, Dr. Tripti Chabra, as the first author. And this work also got a lot of media coverage during its time of publication. And last year, we have done the work for preparing a high carbon biofuel precursor. And in this case, we have used a niobium pentoxide and grafted it with sulfonic acid group for doing the solventless conversion of this biomass derivatives to the biofuel precursors. And this was published in the journal Fuel. Now, moving on to the second part of my talk, which is on organic transformation. And one of the most important organic transformation is the hydrogen transfer reaction. And why catalytic hydrogen transfer reaction is important, or what is the advantage? Because here the hydrogen source which is used is easy to handle. Therefore, the possible casualties are minimized, and we can use mild reaction conditions which can result in enhanced selectivity. And what we have done is we have taken again the same graphitic carbon nitride, and here we have done the chemical oxidation of the graphitic carbon nitride in order to prepare the catalyst. So what does this chemical oxidation do? The chemical oxidation does the it imparts the various hydrophilic functional groups onto the graphitic carbon nitride, which includes the OH functional group, the COOH functional group, and also the C double bond O, the carbonyl functional groups. And these functional groups play an active role as the catalytic active sites for the hydrogen transfer reaction. So therefore, we have used this oxidized form of the graphitic carbonitride nanosheets as a metal-free heterogeneous catalyst for the sustainable hydrogen transfer reaction under mild condition. And this work was done by my former PhD scholar, Dr. Priyanka Chaudhary. And this is how the material was prepared. So we have started with the dicyan diamide and did a calcination of this material to obtain the graphitic carbonitride nanosheets. And this graphitic carbonitride nanosheets was further oxidized in the presence of an oxidizing agent, which is the H2O2, along with the HNO3 and H2SO4, in order to impart the oxidation functionalities onto this graphitic carbonitride. So you can see that the various functionalities like COOH, C double bond O, and also the OH functionalities are being incorporated within this oxidized graphitic carbonitride. And similar to the previous work, we have done a detailed characterization of our material using X-ray diffraction pattern, using Raman spectroscopy, and also using IR spectroscopy in order to understand what is the structure of this material and how and what are the functional groups which are kind of imparted onto this material. We also did the thermogravimetric analysis in order to understand the thermal properties of the material, which indicated that the materials are quite stable up to about 400 degrees centigrade. And we did the morphological characterization using SEM and the TEM spectroscopic technique, TEM microscopic technique, which indicated a sheet type of a morphology for the sample. And we also did the elemental mapping and the DAX analysis in order to understand what are the elements present in the sample and also how they are distributed across the sample. We did a detailed XPS study, the X-ray photoelectron spectroscopic study, in order to understand how the different elements present in the sample are interacting with each other and how they contributed to the overall catalytic activity. And this is the reaction which we explored for the hydrogen transfer, wherein the 4-chlorobenzaldehyde reacts with 2-propanol. Here, the 2-propanol acts as both the protonating agent, the hydrogenating agent, as well as the solvent here. And the product formed are 4-chlorobenzyl alcohol and acetone. So here, this 2 hydrogen atoms which are present in the 2-propanol. So that 2 kind of attack here in order to get the 4-chlorobenzyl alcohol, and acetone is formed as the byproduct in this reaction in the presence of our catalyst. We did a detailed optimization of this catalytic reaction, and wherein we found that with a minimal amount of base and at a temperature of about 80 degrees centigrade, within 4 hours, we were able to achieve 92% of the yield of the reaction. We also did detailed optimization studies, and in addition, we also did the substrate scope studies, wherein we have tried with the reaction with the different carbonyl substrates as shown here, and the corresponding products were formed in the reaction in relatively good yields and higher turnover numbers. And the reaction not only works with the aromatic substrates or even the electron withdrawing or electron donating group containing substrates, but also with the aliphatic substrates. So that information was also obtained from the substrate scope studies. And subsequently, we did the green matrix parameter calculations, wherein we determined the green matrix parameters such as the environmental factor, atom economy, mass intensity, process mass intensity, reaction mass efficiency, and also the carbon economy. And we got relatively good values for each of these parameters, which indicates that this reaction is green in nature. And this work was also published in the journal Green Chemistry in 2020 with my former PhD scholar, Dr. Priyanka Chaudhary, as the first author. And this work also got a lot of media attention during the time of its publication. Subsequently, we did another work wherein we have functionalized this graphitic carbonitride with sulfonic acid functional groups and used it as a solid acid, solid base bifunctional catalyst for Navier-Stokes condensation and also multi-component tandem reaction. And this work was published in Material Chemistry Frontiers in the year 2021, again with Ms. Priyanka Chaudhary as the first author. And in 2022, we did another work based on graphitic carbonitride, wherein we phosphorylated the graphitic carbonitride and used it as a sustainable, selective, and metal-free catalyst for the synthesis of primary amides. And in the middle of last year, in 2023, we have published another work which is based on boron nitride, not graphitic carbonitride, but boron nitride, wherein we have functionalized this boron nitride with hydroxyl functional groups and used it as an efficient and sustainable catalyst for the ipsohydroxylation of aryl boronic acid. And this was published in ACS Applied Materials and Interfaces last year. And again, at the end of last year, we did one more work on boron nitrate, wherein we have functionalized this boron nitrate with sulfonic group and used it for the synthesis of aromatic nitriles under mild reaction conditions. And this was published in Chemical Engineering Journal. And now moving on to the last part of my talk, which is on photocatalytic nitrogen fixation. So nitrogen fixation is a very important reaction because till date, we are using the Haber-Bosch process to obtain the ammonia, NH3 molecule, which is the more cost-intensive process. It is also a process which emits a lot of carbon, and also the materials or the catalyst used are very expensive, and this process involves high temperature and high pressure, so which are all non-favorable conditions. So whereas in this case, what we have done is we have utilized the nitrogen, which can be utilized from air, because air contains a lot of nitrogen. 71% of the air is nitrogen, and we have taken the hydrogen from water, because water is also a plentiful resource, and we have used the light from the sunlight, and in the presence of our catalyst, which is also prepared from earth abundant materials, we have kind of converted this nitrogen to ammonia. So how we have done, we have used a defect engineered leaf inspired calcium titanate for this process, wherein we have taken a leaf, the sacred fig leaf, but basically any leaf can be taken for this purpose. And we have done some pre-treatment of the leaf, and after this pre-treatments, we have prepared the leaf inspired calcium titanate. And the idea behind using the leaf is the leaves are materials which can have better light harvesting from the sunlight. So we can take a lot of inspiration from the leaf in order to better harvest the sunlight from the sun. And we have prepared this leaf inspired calcium titanate, and subsequently we have subjected it to a reducing environment treatment using sodium borohydrate in order to create some defects onto this material. So the impacted defects are mainly the oxygen vacancy defects, and the calcium titanate, instead of having CaTiO3, it will have CaTiO3 minus X. So there are certain oxygen vacancies, and these oxygen vacancies, these are kind of spread throughout the sample at certain locations, and these are the missing oxygens. And because of these things, the oxygen vacancies, there are high charges which are kind of located in these sites, and these sites will form special sites to make the nitrogen adhere onto that, and eventually the nitrogen in triple bond nitrogen, the bond is bent and then broken, so that the nitrogen is available to combine with the hydrogen to form ammonia. That's the story behind the work. So what we have done in this case specifically is, this is how the morphology of the leaf looks like. So you can see a lot of beautiful micro and nanostructures on the leaf. These are mainly
just a small interruption. You have 3 minutes more.
Sure. I'll complete it within 3 minutes.
We are having some more questions also. People are curious.
Sure. I'll be happy to take the questions after the talk.
Yeah.
So you can see that these leaves are very beautiful, not only when we see it, but also it has beautiful micro and nanostructures which are present on them. And these micro and nanostructures are mainly responsible for the light harvesting properties. And when we do the replication of the leaf using our calcium titanate, this is the calcium titanate material which we have prepared using the leaf inspired material, wherein leaf was used as a sacrificial template in this case. So the entire material is calcium titanate, because we have done a calcination of around 800 degrees centigrade, wherein all the carbonaceous material in the leaf is removed. If you do not use it, we end up getting some random sized powders. As like the previous work, we have done a detailed characterization of the sample using X-ray diffraction, using Raman spectroscopy, and also using the EPR spectroscopy in order to understand the oxygen vacancies, and also the XPS spectroscopic techniques. In the interest of time, I'm not going into the more details of the technique, but if there are questions, I'll be happy to answer. We have also done a detailed transmission electron microscopic characterization of the samples, wherein we could see or locate some of the oxygen vacancies on the sample. Subsequently, the sample was first utilized for the hydrogen evolution studies, wherein the water was kind of split into H2 and O2, and the evolved hydrogen was monitored using a gas chromatography. And subsequently, we have utilized the sample for the ammonia production, wherein the nitrogen is brought in, and the nitrogen can combine with this hydrogen to form the ammonia. We also studied the recyclability of our sample. And we did a detailed theoretical analysis using the density functional theory for this work. And this was done in collaboration with the group of Dr. Saswata Bhattacharya at IIT Delhi. And so this catalyst can be used both for the hydrogen evolution as well as for the nitrogen fixation. in very good very good photocatalytic hydrogen evolution can be obtained with STS or to hydrogen conversion efficiency of 1.17. And this work was published in the Journal of Medical Chemistry A with my former PhD scholar Dr. Ashish Kumar as the first author. And this work also got a lot of media attention during the time of its publication. And subsequent to this work, we did yet another work again for the nitrogen fixation. Here in this case, we used pure water without any sacrificial agent. And here we used strontium titaniate as the catalyst for doing this nitrogen fixation. And this was published in Nanoscale Journal in the year 2023. And we also published yet another work on nitrogen fixation in the journal ACS Applied Materials and Interfaces last year in 2023. In this work, my current PhD student Manisha Sharma was the first author, wherein Ashish Kumar also contributed to this work. And based on this and several other works we have done in the domain of perovskite oxides, we have also written a review article on perovskite oxides, which was published in the journal ACS Catalysis in 2020. And which was also featured on the front cover of the ACS Catalysis journal. And we wrote another review article mainly on vacancy engineering for semiconductor photocatalysis, the implications in hydrogen evolution and nitrogen fixation application. And this was published by Ashish Kumar in Advanced Functional Materials. So these two works were reviews were written during the COVID lockdown period. And finally, I would like to conclude by saying that our group is actively working in the domain of heterogeneous catalysis for energy and environment applications. And in today's talk, I was able to kind of give you a glimpse about the works done in our group on biomass conversion, organic transformation, and nitrogen fixation, which was already coupled with hydrogen evolution. And finally, I'd like to thank once again all the members of my research group, faculty colleagues and staffs at IIT Mandi for their kind support, and the research collaborators both within and outside IIT Mandi, and our instrumentation facilities, which is the Advanced Material Research Center, and the different funding sources which has supported our works financially. Thank you. Thank you very much, one and all, from our group. Thank you.
Thank you, Professor, for such a loaded presentation. It was very interesting, catering to various applications all around, and we have already questions waiting for you. So the first question is also this occurred to me also because I also worked on this sustainability metric calculation for nanoparticles synthesis or nanocomposite synthesis. So the question goes like, you showed some parameters that deems a reaction to be green. How are those parameters calculated? The question is from Arpan Bhattacharya. Just adding to the question, like you must have followed some formula, I guess. So my question is like, did you like follow those metric formula which are already existing, or did you formulate it by yourself?
Yeah, these we didn't formulate any formula from ourselves. So these are quite well established green matrix parameters, which are very well defined, and it can be seen in many of the textbooks on green chemistry. And we have utilized the already existing formula in order to calculate all these numbers. And the formula along with the detailed calculations can be seen in the supporting information of our paper. So this is our paper, and if you go to the supporting information of this paper, we have explained each of these parameters in detail, like what is the definition of the parameter, what is the formula which is used, along with one model calculation. We have shown it in the supporting information. So you can look it up in our paper. So in any of our papers which deals with green chemistry and the green chemistry matrix, we have always explained the formula in the supporting information section.
Right. So like I remember when I was doing my PhD work and I was looking for this metric formula, I was going through various reviews where I could see that there was a little bit, like for the same parameter, there might be a bit a varied way of presenting the formula. So how do you deal with that?
Yeah. So we use usually standard textbooks and also standard research articles in order to understand the formula, and we use it to calculate it. And also in the manuscript, we kind of mentioned what is the source from where we have taken the formula, so that if anyone want to know the source, they can easily go to that particular source. And those are that's the way we did it, and we also mentioned what is the formula in the supporting information as well. So so what formula we have used, we have explicitly given. But there may exist another formula, but we are telling that we have used this particular formula to calculate it.
Right, right. Yeah, I'm sure I will have some more things to get back to you later regarding research. The next question which we have with us by Dr. Shayan, he asks, like, during boron doping, is there any change in carbon nitride frame? Is there any probability of carbon doped BN in this case?
Okay. So boron forms a substitutional dopant here. So we are not functionalizing it, so that there would be some small changes in the framework, which we can see it from the X-ray diffraction pattern, wherein there is a shift of the X-ray diffraction peak because of the boron doping. So the boron kind of takes the place either of the carbon or the nitrogen here. So it makes a substitutional doping, and we are able to see the change in the XRD pattern, which we have shown it also in this paper in carbon. So I don't have the XRD pattern here right in front of me, but you can look at this manuscript to see the change.
Thank you. Sangeeta Bishi has raised her hand. So if you want to ask some question, please unmute yourself and ask.
Yes, thank you, ma'am. Actually, the graphite carbonated is the heterogeneous catalyst, and as you are approaching the sustainable chemistry, then my question is that have you checked the recyclability test of this heterogeneous catalyst?
Yeah. Always in all our work, we do the recyclability test. So this is the recyclability test for the graphite carbonitrate, the sulfonated graphite carbonitrate. So because any heterogeneous catalyst, we have to do mandatory type of requirement. We may not get exactly the same yield of the product in all the cases, because here there is a drastic decrease in the yield from the first cycle to the fifth cycle. This is because along with the HMF, we also get to see the humin formation. Humins are the polymerized carbonaceous material which are formed from the HMF. So if we leave it for a longer period of time or over the course of the reaction, the humins are formed. And when the humins are solid products, and the humins cannot easily be washed away while we kind of do the recyclability of the catalyst. So the humins kind of stick on to the catalyst and doesn't go away during the washing. And because of this reason, the catalytic active sites are blocked. And when the catalytic active sites are blocked, obviously the yield would decrease. This is the reason for this case, this particular case. But in all our work, we have done the recyclability studies, and we also do the characterization of the recovered catalyst or the spent catalyst in order to understand whether the catalyst retains its structural integrity or not. That studies also we do.
Yeah. Okay, thank you for clarifying my questions. Yeah.
Do we have any more questions? Rabiul, if you are around. We have one more. So how to calculate the percentage of nitrogen doping?
Okay.
For the nitride framework.
Okay. In this case, we did not calculate the nitrogen doping. Actually, nitrogen is not doped in this graphite carbonitride network. The graphite carbonitride network, the nitrogen is already present on the framework. So it is not a doped one. It is already existing in this framework. So it is already impacted in this case. So in our work, we kind of match the X-ray diffraction pattern of the graphitic carbon nitride with the well-known X-ray diffraction pattern of the graphitic carbon nitride. From that only we kind of tell that, okay, this is a graphitic carbon nitride material. So this GC3 and 4 is already quite well known and quite well established. There are also other higher forms or other different forms of carbon nitride, like C3N5 is also there. C2N7 is also there. There are many other forms wherein the peak, the XRD peak occurs at different places. So those are different materials. C3 and 4 is a very common and easy direct material. And if you're really interested to know what is the amount of content, nitrogen content, we can do this CHNOSO analysis. So we have a CHNOSO analyzer. So it's an elemental analysis technique, so wherein we can find what is the exact ratio between carbon and nitrogen.
Right. Rabiul raised his hand.
Hello.
Yes.
Can you hear me?
Yes. Go on.
Hello. So my question was, you already answered this question. CHH analysis you did or not, and how, because which type of C3 N4 or C3NX? So X, what is the X? I want to know. That's the first question. So
Okay.
you told already it did not measure. So second question is, how much cost will come around 1 per kg of your material if we want to make
sorry,
in bulk?
Sorry, I missed your
for bulk synthesis, how much cost will come per kg of
Oh,
material?
okay. That number I don't have it in my mind, but in some of our publications we have already given that number. But in broadly speaking, we get it in a very good yield. For example, this is the process which we use to prepare the simple graphitic carbon nitride nanosheets from dicyan diamide. So if we use, for example, 1 gram of dicyan diamide, we get quite a good number, at least 500 mg or more than 500 mg of graphitic carbon nitride. So we get it in quite
50%.
Exactly, I do
You
not
can
know.
get it.
Yeah, around 50.
How
Close
much?
to 50%, you can get it.
52. And then we can calculate.
Yes.
Thank you.
Thank you, Professor Venkata Krishnan, for this very interesting and wonderful presentation. I'm sure we will have more questions with us, but then we can always get back to you in case we want some more clarifications. And me personally, yes, of course. So we will. Thank you again.
Thank you very much once again. Yes.
Yeah. We will go on with our next presentation. So our next speaker is Professor Satyaranjan Bhattacharya, he former professor of SINP. So let me give you a brief introduction. He was a former senior professor of surface physics and material science division of SINP, Kolkata. Presently, professor adjunct of ECE Department of Institute of Engineering and Management, IEM, Kolkata. His research activities are primarily material modifications due to energetic ion interactions at different energy regimes for novel aspects of sputtering and sputter-induced phenomena that have immense application in nanomaterials. Size-selected nanocluster production and deposition of functional thin films is his latest research interest. So I welcome Professor Bhattacharya, and yeah, please, the floor is yours.
Thank you for introduction, and I am very happy to present my talk in the third international conference on Convergence of Interdisciplinary Science organized by Science Dialectica. I particularly thank Professor Arup Kumar Das for inviting me. Unfortunately, my camera is not working, so I will share my slides.
Sure.
Yeah. So is it visible?
No, the slide has not come yet.
Now?
No. Sir, are you there?
Yeah.
Yes, we can see your screen, but the slide is not there. But we can see your screen.
Can you see now?
We can see your Gmail.
Okay, just. Can you now see? Huh?
No, sir, unfortunately, it is still the Gmail screen which we are seeing.
Yeah.
Sir, I think you stop the screen.
Saurabh, do you have his presentation? Or
No,
maybe
I
you
don't
can
have.
share this?
Sir, if you want, you can send us also. We can share from our side. Okay, just wait for some time. Okay. What is our schedule time? 3:30.
Yes.
Okay, this year we are running almost in time, right?
By now, I think we are almost like 30 minutes behind.
Oh, 30 minutes. Okay.
Yeah.
If the next speaker is available, we can invite him, so we can come to Professor after some time, right? After the next speaker, maybe.
Yeah, I can check if Professor Suman Ghosh is already here. No, I cannot hear from Professor Suman. Saurabh, can you please call the professor and check?
Professor Suman Ghosh is, I think, he is in means meeting, inside the meeting.
Okay.
Maybe he is not around, but he is in meeting.
And is it possible to call Professor Bhattacharya?
Okay, let me check.
Yeah.
Hello.
Yeah. I think he's there. Okay. Hello, Professor.
Yes.
Are you ready to present right now? Because our
Yes. I can start.
Yeah. Thank you.
Okay. So I think we have lost Professor Bhattacharya right now. He might be fixing this. So in the meantime, maybe we can go ahead with Professor Suman Ghosh with his presentation, and then we can come back to Professor Bhattacharya after this. So in case if Professor Suman is ready, I can introduce him.
Hello.
Yes. So Professor Suman Ghosh is associate professor in NIT Rourkela. He received his PhD from IIT Kharagpur in 2012, and he did his graduation and post-graduation from Jadavpur University. He is a recipient of University Medal during his postgraduate, and his research area includes multi-phase low heat exchanger, natural convection using nanofluid in cavities, inverse method in heat transfer, duct shape optimization in thermofluid systems, supercritical mini channel heat sinks, pulse tube refrigeration, root blowers, fluid power control, and computational intelligence. He has published more than 50 papers in international journals and conference papers. So I would like to welcome Professor Suman Ghosh as our next speaker. Professor Ghosh.
Thank you, madam. So I'm just going to start. First, I'm presenting now. I'm sharing the slide here.
Sir, is it can you is it possible for you to switch on the camera also?
Madam, please forgive me. I was trying from the last half an hour, but I don't know exactly for what reason it is not working at this moment, because yesterday and morning also when I checked, it was working properly. And it is a desktop. So please forgive me at this moment. I'm trying.
No problem, sir.
Is it visible, madam? Please check.
No, the slide has not appeared yet. It's coming. Yes, you can make it full screen.
Yes. I have made it. You please check that whether it's visible in the full screen mode or not.
No. It has not appeared full screen yet.
It's not there.
Professor, you can switch on this this click that button below right side, below that zoom. There is a area is there.
I have done it. In my screen, it is in full screen mode, but I don't know why.
Again, you join. Join means again you reshare that PPT. Maybe it is stuck. Yeah, that's better.
Is it visible now?
Not yet. It might be coming.
It's not working, madam. Is it visible, madam?
The slide has come, but yeah, again, not in the full screen mode.
If it is not coming, we can continue with this.
Yes. Yeah.
Can you see the change of screen? The slide changing, is it visible to you?
No.
Have you changed? Are you changing the slide now?
Yes.
No.
Oh my God. But I have shared successfully and Google is showing the message and it is in full screen mode. Till now it is creating problem.
Yes, the slide has changed now to the second slide, introduction slide.
Okay. That means now it is visible.
Yes, we are seeing the second slide of yours.
Okay. Is it extra line is coming? New line is coming?
No, we are still on the introduction slide.
in the introduction slides, one by one line is supposed to come. Is it coming?
No, there is no animation. We can see the whole text together, the whole slide.
That is the problem. It is not working at all then. Next slide. Next to introduction, is it coming?
No, no.
My God.
Professor, if you don't mind, you can share your PPT also with us so that we can share from our end.
Okay, I'm trying. So. Give me some time. I'm checking the internet speed here.
Sure.
You can check the, I think, last speaker of the session, maybe. Professor Paulas from AMU.
Do we have Professor Palashuddin SK from AMU with us now? Professor Palash?
I can see him. He is in the meeting.
I am interrupting here.
Yeah.
Professor Bhattacharya, we can is in the meeting, so we can try him for now once again.
Okay, okay, okay.
So can you hear?
Yes, sir. We can hear you.
Okay. So now I share my slides.
Yes, sir. Let's see. Yeah, please do.
Can you see my slide?
Sir, we are seeing a blank slide.
Is it?
Yes, we can see the slide now.
Okay.
It is
Can you?
Professor Suman Ghosh slide.
It is Suman Ghosh slide. Professor Ghosh, I think you can try after Professor Bhattacharya. Okay. Since he is available, so he can present, then after that you can present. By the meantime, you can fix your internet or that your presentation issue. I'm sorry, we have to move also.
So can you see my slides?
No, sir, not yet. You start sharing again.
Professor Bhattacharya, we cannot see your slide yet.
Yeah. Now? Not still.
No, no.
Okay, just.
Professor Paulasuddin also is available to present. So shall we move, sir?
Okay.
Professor Bhattacharya, is it possible for you to send the slides, the presentation?
Yeah.
Then
Yeah.
you send us.
I can send it to Muntu.
Yes, yes.
Anyone you send it. I think. Who's presenting?
Yeah, I'm sending.
Yeah. Please do.
Professor Ghosh, are you ready to present your presentation? Because I am seeing the presentation of yours. Hello? Hello, Professor Ghosh? Are you around? Or someone is doing? I think Sitoma, we should move to.
No, but can you remove the slide?
Yeah, you just check it.
Professor Suman Ghosh, are you there? Okay, in case if we don't have Professor Suman Ghosh, we just got a message from Professor Palash. He is available. Professor Palash, are you there?
Yeah. So if you permit me, then I can start.
Maybe we can utilize this time. You can start your presentation and then we can come back to the previous two speakers.
Yeah, that will be fine.
Yeah.
So I am sharing my slide then.
Yeah, sure.
Sitoma, please introduce him.
I will introduce him. Yeah. Can you please share your slide first?
Yeah. So is it visible?
Yes, sir. The slide is coming. Can you make it full screen?
Yeah.
Yeah, perfect. So we have Professor Palashuddin SK from AMU University with us. Let me give a brief introduction for him. So he is currently an assistant professor in Department of Chemistry, AMU, and he did his PhD from IIT Guwahati, and he was awarded SIRE fellowship in 2022, and he worked as a fellow in LMU Munich with Professor Thorben Kortz. He obtained university second rank in his bachelor's and was awarded several awards and scholarships. His main research area is chemistry of luminescent nanomaterials for versatile applications such as sensing, catalysis, and biological applications. He has several peer-reviewed research articles, of course, and his research publications were highlighted by science magazines, blogs, and news agencies. So welcome, Professor Palashuddin, to the conference, and the floor is yours. Please go on.
Yeah, thank you for your nice introduction. So, and giving me opportunity to deliver my talk in this platform. Today, I am going to present my work on the non-metallic luminescent quantum dots based smart material for potential biological and environmental remediation application. So, currently, I am working as an assistant professor in the Department of Chemistry, Aligarh Muslim University. And my department is one of the oldest department in India. It was established in the year of 1911 under the chairmanship of Professor H.B. Duncliffe. So here we are working on chemistry of non-metallic luminescent dots and their potential applications. But currently we are focusing on the environmental remediation and biological applications. And this is the slide of my summary of today's talks, and I am going to talk about it. So before going to the main talk, I would like to introduce about quantum dots. You know, the last year Nobel Prize was awarded in the field of quantum dots, and quantum dots are tiny semiconductor particles which have sizes around 2 to 10 nanometer, and where you can see the quantum magics. That means quantum confinement effect. And this quantum confinement effect also depend on the size of these particles. So how do the quantum dots work? Actually, when light falls on these quantum dots, the electron goes to the excited state, and when it comes back to the ground state, it gives the fluorescence. And you can say that this is a type of excited electron in a nanobox. So this is the bulk semiconductor material, where you see that the valence band gap between the valence band and conductance bands is very low. But when you decrease the size, that means in quantum dot, there is a band gap is increasing, as well as you see that there is a discrete of energy levels. So if we take the example of bulk to quantum dots, you can see when size decreases, as size decreases, the band gap between valence band and conductance bands always increases. as well as there is also formation of discrete energy levels. So these are some application of quantum dots that it could be useful for versatile field, for bioimaging, biomedicine, energy harvesting, and LED bulbs, display cameras, and so on. So now I am going to my original talk, that we are really interested in the non-metallic quantum dots, that is carbon dots, sulfur dots, and main talk is based on this carbon dots and sulfur dots. So now, what is carbon dots? You can define carbon dots as a discrete quasi-spherical amorphous or crystalline fascinating class of non-toxic material which shows the excitation tunable fluorescence, and this is important because of their non-toxic nature. Generally, sizes greater than 10 nanometer carbon dots are called as a carbon nanoparticles. So now, why researchers are interested in carbon dots? Actually, the problem with quantum dots is that this is synthesized from heavy metals, and these metals are very toxic to the mammalian cell at relatively low concentration. And that should need to be replaced by fluorescent non-toxic material. And the solution may be the carbon dots or sulfur dots. C dots actually accidentally discovered by the Scriven and co-workers during the purification of single-wall carbon nanotube in the year of 2004. And based on this observation, the search of non-toxic material continues, and the first synthesis method was reported by Shan and co-worker in the year of 2006 by laser evolution method. And what are the advantage of quantum dots, carbon dots? They have several advantages, that it shows excitation tunable emission, light harvesting capability, excellent water solubility, chemical inertness, low toxicity, easy to functionalize, and outstanding photostability. And today I'm going to the oil contamination. So you know that oil contamination in the marine is one of the greatest severe impact in the marine ecological system. So, and it is very harmful, and there is so many reports, and you can get it in newspaper also. So therefore, what do we do? That we synthesize the superhydrophobic carbon dots using the guava leaf extraction, and then we fabricated the C dots coated cotton, and then we employed this CDC for the removing of oil contamination from the water. So first we characterize the C dots by TM analysis, and TM image here shows that the formation of carbon dots around average size around 2.4 nanometer. And from XPS analysis, we found that that this C dots contains carbon and oxygen, and this carbon have sp2 and sp3 hybridized nature. Then we characterize the optical properties of these purified carbon dots, and we found from the UV visible peak that it shows the pi to pi star transition. This is n to pi star, and this is surface trap transition. And the figure B also indicated that there is a excitation tunable fluorescence of these carbon dots. And from figure C, this is the excitation peak corresponding to the emission maximum. And from also the photophysical properties characterized using the time resolution fluorescence spectroscopy, it shows that this is the mono exponential feed with average lifetime 6.2 nanometer. Then we check the aggregation cost fluorescent quenching of this carbon dots in ethanolic solution, and we found when we add water to it, as the concentration of water increases, there is a formation of aggregation and quenching of the fluorescence. Based on this observation, that is inspired to and or motivated us to use it for the superhydrophobic material. So you see, this is TM image also reveal that the formation of aggregates, and figure B and C also indicated that this is the contact angle measurement of this CDC and carbon dots, and it shows that it has a super hydrophobic properties, and the contact angle above 150 degree. And this is the bare cotton image of bare cotton, and this is the C dot fabricated bare cotton. And this is the further from FTIR analysis, we confirm that this bare cotton is coated with the carbon dots. Then I check the absorption of bare cotton, and we found that when we add water to bare cotton, it soaked it, and when we add oil on the bare cotton, it also soaked, and the contact angle is shown in the below of the figure. Then we employed this CDC for removing the floated oils, and you can find that we use several oils from heavy light oils to heavy oils, and you can see that our CDC can effectively remove this oil contamination oil from these floated oils as compared to the bare cotton. Then we also employed it for separation of light and heavy oils from the oil water mixture, and if we see from this figure that our CDC effectively removed the oils from these oil water mixtures. We check the separation efficiency, it is almost above the 95%. It shows 95% for different oil cases. And then we check the absorption capacity. We found the good result for the silicone and motor oils, and it is around 1100 weight percentage. Then we check the applicability of this CDC in diverse environmental conditions such as pH2, pH12, and low temperature and high temperature such as 10 degree and 100 degree, and different water, tap, river, and sea water. And we found that CDC can practically use in harsh condition as well as chemical environments. And this is the image of this performance of super oil absorbent of CDC in different diverse environmental condition. This is the pH 12, and this is the absorption of pH 2, and this is 10 degree and 100 degree. This is absorption from the tap water, and this is river water, and this is artificial sea water. So from that you can see that the CDC can work in diverse conditions. Then we check that after purification of this water, there is any droplet present, oil droplet present in the water. So we perform the DLS analysis, and we found that the before separation it shows the DLSS peak, but after separation of the oils there is no DLS peak. That means there is no droplet in the water. And then we check the recycled CDC, contact angle of recycled CDC, and we found that it's retained its super hydrophobicity. Then we reuse this CDC for again for reusability application, and we found that it can use for the 5 cycles, and it also retain their separation efficiency above 90% and also above 90%. Further, this CDC then used for the proof of concept application for the separation of crude oil from the oil water mixture for the and you can see from this figure that this CDC can effectively remove this crude oil, floated crude oil, as well as from the crude oil from the oil water mixtures. You can separate it by absorption method, and also you can separate it by filtration method using the CDOT. So I do not show the videos of the filtration method, but it can use for the filtration method also. In this next work, we have also developed a sustainable method for autonomous magnetic microboards using the potato peel drives carbon dots and iron oxide nanoparticles in collaboration with Dr. Amoresh Kumar Sahu. You can see from this figure, I use H2O2 as a fuel of these microboards, and this H2O2 degraded using the C dots and Fe3O4. It forms oxygen as well as OH radical. This oxygen helps in the movement of microboard autonomously, and this radical used for the degradation of toxic dyes. I'm not going to the detailed characterization of this microboard, but I will show the results of this. This figure shows the lateral movement of this microboard in different time interval under the 2% H2O2 fuel. And this is the image of the trajectory of the microboard in different conditions. You can see here. And figure C shows that the speed of the microboard as if you increase the H2O2 concentration. That means in different concentration. And from figure D, you can see the lateral vertical movement of these microboards. And the last figure E shows the average vertical movement of cycle of microboard with increasing H2O2 concentration. Then we use for the malachite green dye degradation and rhodium D dye degradation. You can see this is the time dependent degradation curve plot, and you can see that as time increases, there is a degradation, is also percentage of degradation of dyes is also increasing. So in continuous to this work, we also developed a program logic operation based microbot for degradation of toxic pesticide with the help of Dr. Amaresh Kumar Sahu. In this also, we use the H2 as a fuel, and this that H2 to produce oxygen that help in the movement of this microbot, and the radical used for the degradation of toxic pesticides. And this is the same image of this microbot you can see here, and this is the microscope image of this microbots. And figure D shows the vertical movement of this microbot at different time interval in presence of 1% of H2 fuel solution. Then we employed this program logic based microbots for the degradation of prophenous pesticide. And this figure shows that this is the comparison figure of percentage of degradation of prophenous under the condition of standard condition with microbots and without microbots. And this figure also indicates that this microbot effectively degraded the prophenous, and then we check the percentage of degradation prophenous pesticide using microbot in standard condition. Then we develop the logic based degradation of pesticide using two logic. One is AND logical operation and another is OR logical. This is AND and this is OR logic operation, and we get the promising results. So that means we developed a sustainable method where we use the household waste potato peels for synthesis of carbon dots, and this carbon for synthesis carbon dots, and we developed a microbot that can be used for the degradation of pesticide as well as the dyes, and that could be useful for the industrial refrigerant and degradation of pesticide in water. You know that antibacterial bacterial resistance is one of the prime concerns nowadays, and zero-dimensional nanoparticle is a promising option alternative for this. So therefore, we also developed Higgs-derived carbon dots, and then we use these carbon dots for the antibacterial. We employ these carbon dots to check the antibacterial activity of these carbon dots. So this is the curve, time-dependent growth curve of E. coli using C dots and fixed extracted product. We compare with control as well as fixed extracted product, because fixed extracted product also shows the antibacterial activity. But we found that our CDC more promising in comparison to the fixed or extracted product or control fixed extracted product. And then we check the NBT test, we check NBT analysis, and we found that the CDC CDOTs produce ROS reactive oxygen, and that is the reason or mechanism behind the antibacterial activity. The average MIC value of our E. coli bacterial strain is 110, and for B. subtilis for 120. And also from the same image, you can see that this is the control image of the bacteria, and this is after treated sample with this is the bacteria with the pig-derived CDOTs, and this shows that the bacterial cell death. In continuous to this work, we also developed manganese dope biomass-derived carbon dots, and then we use it for the antibacterial application under different light. So for that, what we did that we synthesize manganese dope carbon dots from the guava leaves derived extraction, and then we employed this MNC dots mediated antibacterial activity and using gram-negative bacteria E. coli under different light like white, blue, and yellow light. And we found that this MNC dot gives very good result under the white light, because it can absorb the whole region of the RGB, so red, blue, green light. So it shows promising result in the white light. So we also check that minimum quantity of doping MN is also enhance the antibacterial activity because of the increased level of the production of ROS. So this is the percentage growth curve under different light, and we found that from this that white light gives much more better result, promising result in comparison to the blue and yellow light. And here I want to mention that we use the MNC dots with the ABTS, and this ABTS work as a shuttler of electron. And then we compare this MNC dots activity with the carbon dots also, and we found MNC dots gives more promising result as compared to C dots. So here we can conclude that we developed that biomass derived carbon dots, which is very effective for the antibacterial activity, and it may be potent. It has potential to replace the antibiotic drug resistance antibiotics. Now I am going to the second part of my talk. So now, what is sulfur dots? You can define it as a discrete quasi-spherical nanomaterials, and
just a small reminder, you have 5 minutes left for.
Okay.
Yeah.
So S dots consist of polymeric core, and it's also have various oxidized sulfur group on the surface. And this is the different schematic of different synthesis properties application of S dots. And then we developed the synthesis method of S dot using the classical method of classical chemistry of sodium thiosulfate, and then we employed it for the separation and discrimination of different metal ions such as lead 2+, cobalt 2+, and chromium 6+. So I'm not going to the details of the characterization. So this is the fluorescence peak, and this is XPS analysis, and TM analysis also confirm the formation of S dots. And then we employed this S dot for the colorimetric sensing and colorimetric sensing of these different metal ions. And from both these cases, we found that our S dot can discriminate 3 metal ions, toxic metal ions such as cobalt 2+, chromium 6+, and lead 2+. And you can see from this color also. Then we this image shows the hue image of S dot, and S dot with cobalt 2+, S dot with chromium 6+, and S dot with lead 2+. And this image also helped you to develop the mobile-based app. And we found the limit of detection for cobalt 2+, 1.57 micromolar, for lead 2+, 1.72 micromolar, chromium 6+, for chromium 6+ is 0.56 micromolar. Then further, we developed mechanochemical synthesis method of these sulfur dots, and that could be useful for the cellular imaging. So I'm not going to this is the PL spectra, and this is XPS spectra, and Raman spectra also confirm the formation of polymeric sulfur. Here, TM image also confirm the formation of this. And then we check the cell viability test under different concentration, 200 to 600 microgram per ml, and this against the normal posted epithelial cells as well as posted cancer cells. And we found it is promising as a non-toxic material. And this is the cellular imaging of this. So in conclusion, this non-metallic quantum dots have potential. It has a excellent photoluminescence property, tunable properties. You can tune it as per your application. You can synthesize it from low cost and abundance starting material. It has versatility, environment friendly. It has stability, excellent stability, and biocompatibility. So that can make these non-metallic quantum dots as a promising candidate for addressing current and technological and societal challenges. Finally, our aim is to develop smart and eco-friendly non-metallic quantum dots for sustainable development goals. So I would like to acknowledge my collaborator, Professor Thomben, Dr. Amarish Kumar Sahu, Dr. Sintu Kumar Samanto, and Dr. Oyen Pal. Also, I would like to thank my PhD student and the PhD student from Dr. Amarish Kumar Sahu as well as Dr. Sintu Kumar Samanto. So I would like to acknowledge Department of Chemistry, AMU, Chairman Department of Chemistry, and funding agency ACRB as well as UGC, and also finally the organization of this conference. Thank you.
Thank you so much, Professor Palash, for this very interesting presentation. And it was so exciting to see that the quantum dots can be used for such various applications, ranging from environmental remediation to sensing. um, uh, I have maybe a question to satisfy my curiosity. So you showed that the quantum dots that you had synthesized, they were used for pesticide degradation. So they do that with the help of H2O2 generation, is what I understood. So I just have this little curiosity. So when a pesticide molecule is probably destroyed, do we also see that the resultant parts that are getting generated after the degradation, how are we sure that those parts are, not harmful, or they are like, like they are okay to be sent off in the environment?
Yeah,
I mean,
yeah.
I may be wrong. Please correct me if I'm
Yeah,
wrong.
yeah, yeah. I did not mention in the presentation, but we have already checked it, and also during publication we have also provided the data of the LCMS mass, and we also proposed the mechanism of this. So we
Okay.
found that ultimately it finally produced the carbon dioxide.
Oh, okay. Oh, then yeah, that is really great if it is giving out carbon dioxide. Um, Thank you. And any more questions from the audience, if there is any? Okay, if there is no more questions, probably let me just wrap up this presentation. So thank you so much, Dr. Palash, again for this very nice presentation, a very interesting one. We will go ahead with our next speaker of the day,
Thank you.
Professor Satyaranjan Bhattacharya.
Yes.
Are you there?
Yeah. Can you hear me?
Yes, yes, we can hear you.
Okay. So first I try to share once again. Otherwise, Mantu will share.
Sure.
Yeah. Can you see something?
We are seeing a blank slide.
Okay, then I request Mantu to share on my behalf.
Yeah, yeah.
Sir, first you please stop sharing, then I will share.
Stop presenting. No.
Yes, stop presenting.
Okay. Okay. So
we see the full slide now.
Okay, thank you. So I'm very sorry for the inconveniences. Anyway,
No
my
problem.
topic of the talk is size-selected nanocluster production by gas aggregation method and deposition to grow some novel theories. So mostly I am involved in the work of single atom ions, and then I extended my activities to cluster ions. So basically we get the charged clusters, and these charged clusters are relatively bigger cluster. Say thousands of atoms are there. So what do we mean by the cluster? So The outline of my talk is like this: the introduction, then motivation, nanocluster deposition system. Actually, I will describe our nanocluster deposition system that is installed in SINP. And with this nanocluster system, we also have in situ XPS, X-ray photoelectron spectroscopy facility. And this is one of the first of its kind in India, such a site-selected nanocluster deposition system. So I will then say something about cluster surface interaction, because cluster surface interaction is important in determining the functionality of the cluster films. So that is important. So cluster growth in the source, I will say something about it, and about our cluster deposition system, and I will give some example of our study using cluster site-selected clusters. I will mention three of our works. The first one is the monodispersed film formation by copper site-selected copper nanoclusters. And then I will talk about something about the growth dynamics of the clusters, how when a film is grown, which parameters are important for determining its morphology. And morphology is the dominant property which is used to determine the property of the film. So finally, and another work I will describe, that is the cluster silver cluster copper cluster interaction with some ripple surface. So we make the ripple surface by ion beam. Actually, it is some when the ions are incident obliquely, we get the very ordered ripple structure, and on that ripple structure we deposited some cluster. And what is the result of this interaction? I will say about something, and finally conclusion. So the next slide will give a brief introduction of what is cluster. So cluster is a combination of atoms or molecules, and it can vary. The number varies from 2 to 10 to the power 6. In our system, we have a bigger cluster. That is, our number of atoms are some 100,000 atoms in a cluster. So if I say the atomic mass of any, say, some particular element is like this, that m equals to 4/3 pi r cube rho, and this rw is the Wigner size cell, Wigner size radius, which is fixed for a particular element. Actually, we are concerned with the clusters of transition metals. So I will limit my talk in the metal nanocluster. And the Wigner size radius is like this. And if I get a cluster of, say, n such atoms, and its mass is, say, x, then x equals to m into n. Now, the number of atoms that is contained in a cluster is like this: n equals to r, that is the radius of the cluster, divided by the Wigner size radius to the power 3. So next slide. In the next slide, I will say something about our motivation. The site-selected nanoclusters are becoming one of the most fast-growing interest in material science. The metal nanocluster are a new class of alternative to metal nanoparticles and quantum dots in nanoscience, because in the nanocluster we will have molecular like discrete energy levels which exhibits novel properties, and that is we can replace nanocluster with nanoparticles. As for the example, metal nanoparticle also possess surface plasmon resonance, which covers only a certain portion of visible light, but the metal nanocluster can have multiple bands covering a large portion of the visible light, and that favors the efficiency of the solar cell. There are many unexplored areas of material science where site-selected cluster film can play important role as far as their properties are concerned. Cluster deposition at various energy regimes and surface structure and morphology can be useful in various applications. Actually, as far as the applications of this kind of things, cluster deposition is concerned, some cluster shows some antibacterial properties like silver nanoclusters. And if it is a site-selected cluster, then we can actually control these properties. And we also, depending on the energy of the cluster, the interaction with the substrate, we get the thin films of clusters that will be useful for many applications. For example, if we get a very high impact cluster deposition film, there the film becomes very smooth, and that can be useful in many applications due to their diffusion and surface activation energy. The film surface becomes very smooth. That is useful in many applications. In the next slide, I will show our instrumental setup, and this is basically a magneton-based nanocluster source. So after the magneton gives us the charge particle for a particular cathode or target. For example, if we use copper target, we'll get copper particles from the magneton, and these particles that has to be aggregated. So aggregation process is something like what we get in the fog or in the smoke. They are aggregates actually coming together, and they get the aggregation form. So similarly, here also we will get the aggregation of this dense vapor of some particular element, metal, say for example copper. Then it will actually form clusters. So I will in my next slides I will show that. So in the production of nanocluster, so we have a magneton source that is in the extreme left side. We have the magneton source. So this magneton, this is a DC magneton. So we can only get the metal clusters, but we also have the RF mode of this magneton, where we can get some semiconductor or insulator clusters as well. So after that magneton, we have a chamber that is called the aggregation chamber, that the pink color one. So this aggregation part is actually from the magneton. the charged particles are coming there, and then there are some, we use some cooling agent. For example, we actually flow cold water or liquid nitrogen as we require, and that way clusters are formed, and then these clusters pass through a very fine nozzle, and thus we get the all possible sizes of clusters. So, and this is actually the picture of our system. So this is the we see in the left side of the picture. We have this part is the magnetron and aggregation zone. This part, what Montu is showing, and at the right of this we have a load lock chamber. That yes, there is a load lock chamber. So where we get some samples or preparation part. Because this chamber, the main chamber is a ultra high vacuum chamber, so we mostly use the load lock chamber for introducing our samples and other gadgets. And at the opposite to this part, the same picture, no, not in that way. So opposite to this part, there is actually it is not showing. There is the XPS, and X-ray gun is shown a little bit. It is no, not this part. That is no, this one. This one is the goniometer, and yes, this part is the X-ray source for our XPS analysis. And in the we have the hemispherical electron analyzer that is shown, and the whole instrument was purchased from Oxford Applied Research, and they made it customer designed for us because we wanted a cluster facility, site selected cluster facility, along with in situ XPS analysis system. So this was installed in 2010, and then for selection of the cluster, size selection or mass selection, we have a quadrupole mass filter, and the mass range is 50 to 3 into 10 to the power 6 AMU. We also have a DC ion source for etching our samples for preparation of the samples, and also we can also a little bit sputter cleaning, and also we can do some sputtering experiment also. And in the XPS system, we have twin anode, aluminum and magnesium, and the hemispherical analyzer is 150 millimeter mean radius. And the next slide will show what is gas aggregation. So now go to the gas aggregation. This in the gas aggregation, we also get some other in the aggregation chamber, that I showed earlier. We can change the length of the aggregation zone, and depending on the length, we can get the efficiency of the aggregation and also the cluster size and cluster how it is efficient for a particular metal. And so There are classification of cluster surface interaction. The first one is soft landing. Actually, soft landing means the cluster will deposit on the sample on the substrate with zero energy. But in our case, we cannot do zero, go to zero energy. What happens? There should be some minimum energy. So we can turn the soft landing as 0.1 eV per atom kind of energy. Actually, to get the zero energy, one has to decelerate the beam. The cluster beam, when it is accelerated, because from the quadrupole mass filter, the cluster ejected with certain energy. And at the before the deposition, we can use some bias by some repulsion. For example, if the cluster beam is positively charged, and we can put a positive voltage to the substrate, and by that way we may get some soft landing deposition. But in our case, we did not have the facility to decelerate the beam, but we accelerate the cluster at minimum energy, so that we can assume that it is giving us a very small energy deposition, which is called the soft landing. So in this slide, we have the classification. So in the low energy or soft landing, the cluster is almost intact. There is no shape or size changes. So this is sometimes this kind of soft landing is necessary for a particular reason, for our experimental purpose or for some application purpose. Then we have the medium energy of impact. So here the energy is 1 to 10 eV per atom. So in this case, the cluster are after impact, it actually either diffuses or with the impact it actually get the shape changes, actually flatten sometimes, and also sometimes some atoms can be implanted. The next one is high energy implantation, high energy impact. Here we see the clusters are actually here it is not shown, but some are can be also implanted, some are ejected, and we will get a very fast diffusion of these atoms, and this is why we may get a very smooth film. So the next slide is about our that aggregation zone where the clusters are formed, which I already have described. And the picture below one is the mass filter. So we use the quadrupole mass filter. We have already learned this from Professor Chakraborty's talk. Here the clusters are entering the quadrupole, and in this quadrupole, two opposite rods are in the same voltage. One is with DC volt, another is AC volt. So with this, we see a very helical kind of thing, which is this trajectory of the ions, the charge cluster. This trajectory actually obey the Matthew equation, and if if it does not obey the macro equation, then